mostly concerned with the basic linear algebra calculations. So given a matrix A, like we just pretend it's square for now, it can be just real. How can we compute A times the column vector X quickly? And equally important, how can we apply the inverse of A to X, assuming A is invertible, quickly? So what do we mean by quickly? So for A times X, of course, you know, it's an n by n matrix. If you try to do it by the naive method, it'll take you about n squared operations, by which I mean both, you know, multiplications, additions are counted equally nowadays. And if you try to compute A inverse X, you know, naively, you'll end up with an n cubed operation, assuming you do, for example, Gauss elimination. So those are considered the naive algorithms, and that's what you would normally get in MATLAB or any of the standard linear algebra packages. And of course, you know, people have tried to make these things go faster and faster. The big, of course, surprising result in this area was in 1969 by Strassen, because he showed that when we multiply two matrices, square matrices A and B together, you would normally expect to take n cubed operations because there are n squared inner products to compute. Each inner product takes n operations. But he showed that surprisingly, you can actually cut it back down to n to the power log 7 to the base 2. And that started a whole intense activity in theoretical computer science, and that's not my community. And right now, the best matrix multiplication is around n to the power 2.3. And Strassen, of course, titled this paper as Gaussian elimination is not optimal, not fast matrix multiplication. So in particular, this implies that you can do A inverse times X, also n to the power 2.3 flops, something. Okay, so right now, the best number is 2.3 something something. Okay, but the conjecture is that you can bring it as close to n squared as you wish. And so these are, I will call these algorithms as Strassen type algorithms. And in this, whose conjecture? I believe it's Strassen's conjecture. So in this tutorial, we're not concerned with that kind of. I'll start the tutorial off by saying a few slides about Strassen material and why I'm not that interested in it. What we do care about in this tutorial is that if I know something more about the entries in the matrix A, then can we exploit that to go faster, right? So if suppose A is Topless matrix, then current packages usually just ignore it. And the question is, can we do better? And how can we do better? And there's been a lot of recent work, exciting work in this field. A lot of it came out of analysis rather than algebra. So maybe it's still interesting to this community. Okay, so let's go. So this is the basic outline of the talk. I'll give some examples of what I mean by structured matrices. Then I'll cover some classical topics, the FFT and Topless matrices and polynomial arithmetic, which I feel kind of a little bit embarrassed talking about polynomial arithmetic here, but it's good to be on the same page, I guess. I'll go through it quickly. Then I'll talk about more modern developments, like what's called the displacement rank structure, and then talk about the low rank structures, especially the sequentially semi-separate representations and the hierarchically semi-separate representations. And along the way, maybe I'll try to talk about some open problems too. So what are the examples of structured matrices? So these are not general matrices. The ones that we'll mostly concentrate on, especially in the beginning before I switch to more complicated structures, are Topless matrices, which everybody here is familiar with. So you know, it's a matrix which is constant along all the diagonals. And then, of course, random walk matrices, to which you definitely don't need any introduction. Then Cauchy matrices, which, of course, in every computational algebraist has seen it by now. Then, of course, the whole family of sparse matrices. So these are banded matrices, for example, and then any variation of sparse matrices. To be fair, because I'm an engineer, my main concern, of course, was with sparse matrices. But still, the way the modern theory goes, at least, is that it involves all of these. So we will mix them all together. Of course, we're not interested just in these simple structured matrices. If that was the case, then I don't think the problem would be as interesting. We really are interested as you mix and merge these matrices together. So any operation like this involving where A, B, C, and D are structured matrices is still a structured matrix in my book. And I'm still interested in asking about these operations. So for example, if I give you Topless plus Topless times Topless inverse times Topless and ask you the inverse of that to be applied quickly, I still want that to be done quickly too. So right, of course, as we keep layering it up like this, the structure becomes more and more complicated, and we still want to have fast algorithms for these guys, right? So of course, then also there's always the block versions of this, which is important in engineering. So we have block Topless and so on and so forth. And then generalizations of Cauchy matrix are super important for us. For example, in the Cauchy matrix, the kernel is 1 over x minus y. We'll be interested in other kernels like log of norm of x minus y, and even more complicated kernels like this. So as we go to these, of course, more kernels coming from analysis, the algebraic structure becomes rapidly more complicated, and we might be forced to give up some exactness along the way. Okay, then of course the last bugaboo, which is plagued this field for a long time and has essentially remained open, is when you look at sums of tensor products of these structured matrices. That's really how it arises in engineering, and there most methods just fall apart completely. And I would say that essentially the problem remains completely open when you look at sums of tensor products. Okay, so I would say that much of the field is relatively open. Okay, so once you get into structured matrices, then you can ask asking much more sharper questions, and again most of these would remain open too. So for example, many of the matrices I showed in the previous slide had only n numbers to describe an n by n matrix. So one can naturally ask, if I'm doing AX or A inverse X, can I get up to say n times log to some constant times n? So these class of algorithms are usually called super fast algorithms sometimes, because many times people only speed it up A inverse X from n cubed to n squared. And there are good reasons to do that. Sometimes when we go all the way to n log n, we lose numerical stability. So they're not practical algorithms. And if you give up a little bit of complexity, you can recover a practical algorithm sometimes. Okay, so this is very case dependent, and I'll try to give you a flavor of when this happens and when it's okay. Of course, other than AX and A inverse X, there are other things that we would like to speed up too in practice. We would like to speed up just the factorization itself, the Gauss elimination. We'd like to do Gram-Schmidt QR factorization, the singular value decomposition, or eigen decompositions. All of these are important. But of course, as we leave the LU factorization and go to these more complicated decompositions, it becomes harder and harder to find fast algorithms. And in fact, pretty much finding the structure of these, the eigen decomposition, finding the structure of the eigenvectors, these structured matrices is very much an open problem in general. So all of these are important, and very little is known. And hopefully, I'll try to touch upon the things that we do know something about. Okay, so we're going to go back first and talk about Strassen-style algorithms, because it's always something that's hanging around, especially in the theoretical side of things, and it's good to get an idea why I'm sort of not going to pay too much attention to it. Okay, so Strassen's algorithm is an algorithm for multiplying two matrices quickly. In general, we just pretend the n by n matrices. And Strassen's idea is a very simple idea. So if I take matrix A and B and I roughly split them to 2 by 2, so n over 2 on one side, n over 2 on the other side, and I split it all the way like that conformally, then you notice that to find the block matrices C11, C12, C21, and C22, I need roughly 4 matrix multipliers of size n over 2. Sorry, 8 multipliers totally, so the 4 C's and 2 multipliers for each of them. So 2 times 4 is 8. And I need roughly 4 additions. And Strassen observed that each of the multipliers requires n cubed operations, whereas the additions only require n squared operations. So his idea was that if you could trade some of the multiplies and replace them with additions, then you could get a faster algorithm. And actually, Strassen succeeded in doing this. He showed that for this particular 2 by 2 block case, you can reduce the number of multiplies from 8 to 7. And once you do that, you get a faster algorithm, because you apply the algorithm recursively again and again and again. So you get n to the power log 7 to the base 2. So n to the power log 8 to the base 2 would have been n cubed. He could make n to the power log 7 to the base 2. And that's how he got the first speed up, right? So the Strassen-style algorithms are going to be inherently slow. And my only purpose of this slide is to say why I think it's going to be slow. Okay, so this is not the traditional way to look at it. It's well known now that the way to study Strassen-style algorithms is to look at the 3 tensor corresponding to the bilinear form for matrix multiplication. So I won't talk about that at all. So the idea of Strassen is that you first segregate the multiplies separately. So the matrix M sub L, if you notice that these are intermediate quantities that I'm going to compute to multiply A times B. And I'm going to block partition the matrix A into P by Q blocks, the matrix B into Q by R blocks. Therefore, the product matrix C is going to be P by R blocks. Okay, so it's block matrix multiplication. And I'm going to think of my algorithm as going in 2 stages. In the first stage, I compute some linear, I'm assuming that all the blocks are the same size, so I can freely add them. Okay, just to simplify the way you think about the problem. So I'm going to take some linear combination of the A's, linear combination of the B's. Okay, so this all just involves addition, so they all n squared operations. I just forget about them. Then I do one multiply to find each m. So there are capital L m's I'm going to compute, m1 through m sub capital L. So that capital L matrix multiplication I have to do, right? And then I do some more additions, some linear combinations to form the terms that go into the block matrix C, the final product, right? So in this algorithm, there are exactly capital L multiplies that I'm doing. And what you want to do is to find these constants, alpha, beta, and lambda, such that the final answer is correct. So this is actually matrix multiplication. right? And you control the complexity by picking that capital L. Okay, how big should you pick the capital L? Well, if I did the naive way, then I would require P, Q, R capital M's to be computed. So you want to pick capital L to be strictly less than P, Q, R. Okay, so that determines the number of terms you want, right? So if P and Q and R were 2, then P, Q, R is 8, capital L would be 7, was for Strassen style, right? So you go back and you plug in all the M's over here, you'll get, right, and this side, the equations in AIK, BKJ is fixed. You plug in M, you'll get an equation AIK, BKJ. You compare terms on both sides, you'll get equations involving alpha, beta, lambda. All right, and the number of equations and variables you can write down over there. There are that many variables and that many equations. You'll see that in general, if you don't pick P, Q, and R to be 2, the number of variables is less than the number of equations in general. Okay, of course, this is a trilinear system of equations, and the question is, can you find P, Q, R, and L such that these equations have a solution? Okay, so it is known that, of course, Strassen gave a solution when P, Q, and R and L were all P, Q, and R were 2, and L was 7. In general, the hunt has gone on for finding P, Q, R, and L's which have a solution, right? And most of the results in this field, at least as far as I know, of the existence type. They say there exists a P, a Q, and R, and L for which there is a solution. People very rarely actually produce a solution. It's fiendishly hard to find these solutions, right? But the key point is this: you got to take bigger P's, bigger Q's, bigger R's to enable solutions to occur, to make that bound smaller and smaller and smaller, right? And of course, the bigger the P, the Q, and the R, then the larger the matrix. Because remember, this is a block partitioning that you must use recursively. The larger the smallest matrix can be before which this reaches any savings at all, right? Because we're doing more and more additions as we go along. So current standards are the P, Q's, and R's are so big that we cannot actually think of using them in practice. In terms of practice, I think things that are close to the original Strassen style algorithm is about all that we can hope to do. Okay, so because of this, that these numbers are going to be so big, and they're not very useful, especially I would think in computational algebra where we cannot go to such large matrices. I will ignore Strassen style accelerations. There definitely are papers out there that take the algorithm that I'm talking about and say how to merge Strassen style methods into them and improve the complexity further. Okay, so those kind of technical details I will not talk about in this talk. Okay, so what will I talk about? So before I can go on to what I will talk about, I need to just quickly review the classical stuff. So the classical stuff, is fast polynomial arithmetic, and they in turn are tied to the FFT and Topless matrices. So we'll just jump into it. Right. So the Fourier matrix is the familiar. Everybody knows about the Fourier matrix. So omega sub n is the nth root of one of the nth roots of -1. So I just picked that one, and I make this particular definition. So just the corresponding van der Waals matrix. I took a normalizing 1 over square root of n to make it a unitary matrix. And we define this diagonal matrix, which uses the 2nth root of 1. Okay, and it's well known that if you take this Fourier matrix, that it has this factorization. So it's not true for general van der Waals matrices, but for the Fourier matrix, a general van der Waals matrix almost has a factorization like this. It doesn't quite work out. So you can't just imbibe this technique into van der Waals matrices. But for the Fourier matrix, it splits like that into 2n over 2 by n over 2. So if n is even, you can split it like that. And of course, n is an exact part of 2, n equal to 2 to the power k. You can keep splitting like this. And you notice that the leading term is essentially a tridiagonal matrix. It's got diagonals on the main diagonal and then the 2 off diagonal on the diagonal. So multiplying by these diagonal matrices is a linear operation. And the splitting essentially says that you can keep factorizing this into products of almost diagonal matrices. And then if you multiplying by f is multiplying by this sequence of diagonal matrices, and you can, if you're careful, you can do this in n log n operations. Since f is unitary, its inverse is just a Hermitian, so the same factorization holds. So you can apply by f inverse also in n log n flops. Right? Everybody knows about this. Okay, so the case n not equal to 2 to the power k, I will just cover along the way. All right, so this is the basic idea. So you do divide and conquer, you split into smaller matrices, and then you repeat yourself. Okay, so the next key matrix, of course, in this way of thinking is the circular matrix. So these are Topless matrices which have the circular symmetry. So each row is the circular shift of the row above it, or each column is the circular shift of the column before it. Right? So of course, what goes along with this matrix is this elementary circular matrix, where the ones along the lower diagonal and one on the upper right, the circular matrix. This is a permutation matrix. If you apply this to any column, it will shift all the entries down and move the last entry back to the top. So it's a circular downshift matrix, right? So what is nice is that the circular downshift matrix is diagonalized by the Fourier matrix. Everybody knows this, and I've just written the decomposition on the top over there, right? So since, therefore, multiplying, so since we can decompose the circular downshift matrix into the Fourier matrix, it immediately exposes us to a fast technique. So in particular, because circular matrices can be written as linear combinations of powers of the circular downshift matrix, right? So if I take z squared, then these ones will come down over here and you get 2 1s over there, right? And that will give you the coefficient for C1, for C2, sorry, like that. All right. So this is the coefficient for C1 and so on. So you have this, trivially that can be written like this, right? And since we can diagonalize the z, and this is just the sum of those guys, you can immediately compute that this can be diagonalized with the Fourier matrix with this guy in between. Notice that you just have to apply the Fourier matrix, the first column of the circular matrix, so that can be done in n log n flops. So therefore, from this decomposition now, you can apply any circular matrix, as long as even 2 power k in n log n flops. Okay, so circular matrix can be applied, and of course, therefore, from this is a diagonal decomposition, so we can apply the inverse of any circular matrix as long as the size is 2 to the power k in n log n flops too. Okay, what about if it's not an exact power of 2? Well, that's an easy fix. You notice that I can always pad out the circular matrix, for example, by adding some zeros and keeping the circular structure. So for example, here I'm trying to multiply 3 by 3 circular matrix with x, so I pad the x's with some zeros, embed this whole thing in a circular matrix that's of size 8 by 8. And then after doing the multiply the circular matrix, I just keep the top 3 entries to get the actual product, and I discard the rest. Right? Therefore, since I can always embed any circular matrix in one that is of powers of 2 size and not too much bigger than the one that I started with, I can multiply any circular matrix in n log n flops. All right. Now, what about Topless matrices? So Topless matrices look like this. They're not circulant, but I can always embed a Topless matrix into a circular matrix. So here I showed it, embedding a 3 by 3 Topless into a circular matrix now. Right, the size will be roughly twice as big. And then to get the multiply with x0, x1, x2, I pad it with zeros, multiply, and I keep only the top 3 numbers. Therefore, I can multiply by any Topless matrix in n log n flops too. All right. However, unfortunately, and this is, in my mind, still a very annoying open problem, this technique does not tell you how to apply T inverse in n log n flops. Okay, nobody's ever suggested we could do something along this direction. I don't know why, but it's not doable this way. All right, so it's a much longer route. So once we can do Topless matrices, we can finish off the FFT too. If I take this particular diagonal matrix over here, gamma n, and multiply on both sides of the Fourier matrix, then you're just completing squares inside the Fourier matrix, and the Fourier matrix will become a Topless matrix too, after multiplying by this diagonal scaling. Since it's a Topless matrix now, and I know I can multiply by any Topless matrix in n log n flops, it automatically follows that I can also multiply by any Fourier matrix in n log n flops. Okay, so the Fourier case, like you see in a couple of slides, we can do the multiply, right? So the only thing that's left open is how to multiply by T inverse. The full T inverse is kind of of course, as everybody here knows, it's kind of difficult to do, but we notice there's an easy case. If I have an upper triangular Topless matrix or a lower triangular, doesn't matter, I can apply the inverse of an upper triangular Topless matrix in n log squared n flops. Okay, so you can see how to do this. If I try to do an upper triangular Topless matrix inverse, I first solve T2 x1, so T2 inverse x1, and then I multiply by T1, take it to the right hand side, and multiply by T0 inverse. The key thing to observe is that to do this calculation, you need to solve 2 upper triangular Topless matrices roughly half the size, one involving T0, one involving T2. Of course, T0 and T2 are the same, depending on how you cut them. So the exact power of 2, then they would be the same, otherwise they would not be the same. So I call them T0 and T2, right? And then, of course, you need to multiply by T1, but that's multiplying by Topless matrix. That's an extra cos of log n. So the recursion, if you do this by divide and conquer technique, the total number of flops f of n will be 2 times from the size n over 2 plus the cost of moving x1 to the right-hand side. So that's the inequality. Of course, if you solve that inequality, you'll see that f of n is at most n log squared n flops. Right. So multiplying by the inverse of upper triangular Topless matrix is quite trivial to do. All right. So now So those are the easy ones. With that under our belt, we can immediately see that we can do all of most of the polynomial arithmetic also in a few slides too. Okay, so the easy one, of course, is multiplying two polynomials, one with coefficients a, one with coefficients b, to get the coefficient c in the monomial basis. This is just multiplying the column b by the Topless matrix involving the coefficients a, so that we can do an n log n flops. Okay, so matrix multiplication is out of there. The next one is the division, and this, of course, where everything starts going south. So if you want to take a polynomial c and divide by polynomial a, all right, and the quotient is q and the remainder is r, so that's what it looks like, right? So a times, so we want to find q and r, and typically it's set up like this. So everybody's here familiar with this matrix formulation of this. So this is what it looks like. It's conventional to ask that the higher degree terms are 0. You can clearly, we're just doing Gaussian formations, you can ask for whichever one is 0 or not. But typically we ask either, it's high degrees are 0 or low degrees are 0. Those are two conventional things. Either we put the 0 on the bottom or the 0 on the top. It's irrelevant. But now we see that in either case, this is a bad idea numerically. Because if I do it like this by putting all the non-zero remainders on the top and asking for the bottom equations to be exact, then I'm solving a lower triangular system with AP on the diagonal, right? And of course, those can become very small. If I make the other extreme choice by moving all the zeros to the top and moving r's down, I'll be solving a lower triangular system with a zeros in the diagonal, and a0 can be small compared to the other coefficients too. So either way, it's pick your poison kind of approach this way. As soon as you go for division, you're going to cause division by badly conditioned matrix in general, and you're going to start getting large numbers showing up in the Q's, and then as a result in R's. Okay, but anyway, this is the conventional thing, so I'm just going to talk about it. Okay, but this is already going to cause us headaches because we'll repeatedly use this division algorithm in the classical stuff. Okay, so anyway, we have the main thing is we're just inverting this upper triangular Topless matrix, so we can do that in n log squared n operations. Then computing the remainder involves multiplying by the upper triangular Topless on the top. That's an additional n log n operations. Okay, so that's easy. Okay, now really a few more polynomial arithmetic stuff left, so we'll just polish it off. One thing is to expand a product of linear terms. So I just follow this notation. I guess it's my own, but if I give me n complex numbers x0 to xn minus 1, and I want to form products involving the numbers from xr to xs, I call it qr colon s. Okay, so that's a product of just a few of those terms. How can I do that quickly? So you want to find the coefficients in the monomial basis. How do I do it? So the key idea is again a divide and conquer style technique. You notice that if I take all of them from x0 to xn minus 1, that's q0 n minus 1, I can split it down the middle roughly at n over 2, find the products involving the first n over 2 factors and the product involving the last n over 2 factors, and then multiply them together. So this tells you directly this is a divide and conquer technique is available. You do each one separately, then multiply, and you go to the calculations again, and it's n log squared n flops, because we know how to multiply two polynomials in n log n flops. Right, so that's n log squared n. Okay, that's the trivial one. The key thing to observe in this is that all the intermediate calculations are used in later computations. So for example, when I'm computing q0 to qn over 2, I also compute q0 to qn over 4, for example. And those already computed along this divide and conquer technique. And all of these polynomials are used later on calculation. Okay, so I can use all of them for the grand cause of n log squared n flops. Okay, and that's how at least one way of thinking about the classical stuff. All right, so let's look at polynomial evaluation now. So I've given a polynomial degree p, a polynomial p of degree n, and I have n points x sub 0 to x sub n minus 1, and I want to evaluate p at each of these x sub i's. Right? If you use Horner's rule, it'll take you n squared flops, but you can do it in n log squared n flops, n log cubed n flops, at least by this method. So the idea is very simple again. You divide p of x by q0 n over 2, right? You get d0 plus p0, and you notice that if you want to evaluate p at the first n over 2 points, then d0 does not play a role, only p0 is needed. So it should be p0, p1. Okay, mislabel that. Similarly, if you want to evaluate p of at the last n over 2, you will need p1. Okay, and because p0 and p1 are roughly half the degree, you have a divide and conquer style technique again. So you can take half the points, value on a polynomial degree half of what you started with, take the other half of the points, another polynomial degree n over 2, and you do this recursively again. Right, so you keep breaking it down. And the polynomial that you need to divide by are these q0s, which we have all of them already at n log squared n flops already. So, and then we know how to do polynomial division in n log squared n, so the whole thing is already set up. It's a matter of just sitting down and churning it out. Eventually, you find that the complexity is n log cube n. Okay, but again, notice that we had to do polynomial division, which is already a disaster to start with. So this is not going to be really quite a feasible method, but gets the complexity out of the way at least. Then finally, the last one is polynomial interpolation to go backward from evaluation. So we need to talk about Lagrange sums. For Lagrange sums, we need these monomials where I'm taking all the roots from xr to x of s, but I'm skipping the one at t. So I skip the point x minus xt in that factor. That's what that r colon t colon s means. Okay. So I'm interested in sums of the form p of x, where I take all the products q0, x minus x0 to xn minus 1, except I skip the ith one and I multiply that by the number ai, and then sum over all i's. Okay. So we are interested in sums of that form, and we want to evaluate these sums quickly. Okay, so the key thing is to observe again that there's a divide and conquer style technique. If I look at products x minus x0 up to xn minus 1, where I skip the ith one, and I is always from 0 to n minus 2, then you notice that the last, from x of n over 2 to x of n minus 1, those terms remain common. Right? So you can factor those out, and only the skipping happens in the first half. Similarly, if I look at I bigger than n over 2, then the terms I'm skipping lie on this side, and the first x minus x0 up to x minus xn over 2 terms remain constant. Right? It's this constant factor. So I can split it like that. If I substitute this back into p of x, I see that whole sum splits into two Lagrange sums of degree n over 2 instead. Right? So we have the splitting we want. The splitting is done over these polynomials, which I've already computed already in n log squared and flops. Right? So the splitting can be done, and then you just use this idea again. Just a lot of elbow grease after this point, but that's the basic idea to split, and the whole operation takes n log squared n. Okay. So you can write any Lagrange sum of that form. Because we can, if there are any Lagrange sum of that form, then we can do interpolation, because Lagrange gave a formula for interpolating p of x if you know its values at p of x0, x1 up to xn minus 1, and p is of degree n. Right? That's the formula. You see, the only wrinkle that we have to address is how to evaluate the denominator of that term over there, but that's also well known. We know well that if I drop the ith term from x minus x0 xn minus 1 and write x sub I, the term that I dropped, the same thing as taking all the products, differentiating it, and then evaluating x sub I. Right? So that simple observation tells us how to do the calculation. Given a polynomial, in monomial basis, we can compute the derivative in linear term, right? We just differentiate term by term. It's actually O of n operations to compute the derivative. But once you compute the derivative, then we just evaluate that polynomial at x0 to xn minus 1. But I already said how to evaluate polynomials in n log squared n flops, or cubed n flops. So that's the whole complexity. All right. So that finishes all the classical polynomial stuff. Right? And the key thing is to observe is that for any of the non-trivial ones, we went through polynomial division, at least in this way of doing things. And that's going to cause these large growth factors, depending how small a0 or ap or anything like that along the way is. Because we're doing divide and conquer, you're going to get other coefficients which can be small too, which means that in exact arithmetic, you're going to need a large number of bits to store all these coefficients. If you're doing in floating point arithmetic, it means these algorithms are numerically unstable. There have been papers trying to come up with other algorithms for fixing these issues, so we can look it up in the literature. But as far as I know, the state of the art is that there is still this fairly large growths in these type of algorithms. Okay, so now we're going to go to the more modern approaches to looking at these structured matrices. Okay, so one is the displacement structure. And of course, there are algorithms for dividing, applying the inverse of Topless matrices quickly, but they're also unstable. And finally, these algorithms, these division by Topless matrices, were made stable through a very long and roundabout route. Okay, they started with the development of the notion of displacement rank by Kailath and his co-workers. And after many years, like over a decade or so, these ideas finally led to ways in which we can now have almost linear time, numerically stable, fast algorithms for applying the inverse of a Topless matrix to a column vector. Okay, so it's a long route, and I just can give you some flavor of how these things were eventually achieved. Okay, so the basic idea is very simple, so I'll just explain it by example. So now I define what's called this downshift matrix. Notice it's closely related to the circular downshift matrix, except the top right corner is not a 1 anymore, it's just a 0. So this is not a permutation matrix. In particular, it's not invertible. So if you apply this matrix to a column vector, it shifts all the numbers down by one step and introduces 0 on the top entry. Okay, so it's not invertible. The key thing about this downshift matrix is that if I apply the downshift to a Topless matrix from the left, it moves the Topless matrix down by one row. And if I apply the transfer from the right, it moves it to the right by one column. And then if I subtract it back from the Topless matrix, you see that I knock off this submatrix over here, introduce all these zeros. So this operation only leaves the first row and the first column of the Topless matrix untouched. And therefore, the right-hand side of this linear operator will always be a rank 2 matrix when you apply to a Topless matrix. Okay, so this will always be a rank 2 matrix, at most rank 2. So this is called the displacement rank. And because we're displacing the Topless matrix along the diagonal, that's how the word displacement was chosen. Okay, so this is the canonical example. And the idea, of course, is that this linear operator on the left acting on this Topless matrix is actually invertible. And not only invertible, you can actually invert it very fast. So because of this, we can use the right-hand side as a surrogate for the Topless matrix, right? But of course, this is a very poor surrogate in some sense. This is such a roundabout way of denoting the Topless matrix, but it's got some really, really good properties which I'm going to talk about. Okay, so this displacement structure applies not only to the Topless matrix, but also to some of the other classical matrices. For example, we take the Van Neumann matrix. You can pick other operators in there. For example, pick D to be a diagonal matrix of all the x's that you see. So x0, x1, x2 along the diagonal. That's the matrix D. And if I multiply the Van Neumann matrix from the left by this diagonal matrix, right, you see that essentially I'm increasing the power of each column by 1. Then if I shift it to the right by the downshift matrix and the transpose, subtract from the Van Neumann matrix, I cancel everybody except the first column. So therefore, the right-hand side of this matrix will always, of this operator will always be a rank 1 matrix if V is a Van Neumann matrix. And I pick this D according to the matrix V. Okay, so we call this the displacement rank of the Van Neumann matrix. Same thing for the Cauchy and the pick matrices. If I look at the Cauchy matrix, for example, and I multiply by this diagonal matrix and subtract from C, you will always get this rank 1 matrix. Okay, so the Cauchy matrix also has displacement structure rank 1, but with different coefficients. Okay, so motivated by this, you are motivated to make the general definition of script L underscore ABT to be the displacement operator T minus ATB transpose. Okay, and typically we're interested in the rank of the right-hand side. So normally I'll write the rank as PQ transpose, but P and Q are supposed to be some rank-revealing factorization on the right-hand side. And we assume the rank is called R, and we usually call this R as the displacement rank of this matrix T with respect to the displacement operator whose coefficients are A and B. You can look at more general operators of the Sylvester-Stein type, but you also have coefficients in front of T, but it's not necessary in this tutorial. Okay, you can generalize a little bit. What you cannot do, of course, is that you cannot go to 3 terms for well-known reasons, right? The spectral structure of those operators are not known. So you're stuck with this 2-term approach. All right. So the key thing is that as long as you can apply this operator rapidly to a rank 1 matrix on the right-hand side, the inverse, this is a useful way of thinking about the problem. Okay, and that's what we're going to concentrate on. Okay, so the displacement structure theory is, I should say, is like a grab bag of techniques. It doesn't have quite the flow of the technique that we'll talk about later on. Okay, so it's a little bit of expert attention required. Now, when you're working with displacement operator, we want to compute, apply T to X, T inverse to X, and with L factor of T, and so on and so forth. And we always want to keep the displacement structure around. Okay, so what are the operations that will preserve the displacement structure? Well, as long as you're multiplying T from the left and right by invertible operators, you see we can write in a new displacement operator for the new T, as long as you do a symmetric transformation on A and B involving W and V. Okay, so that's the key thing. So when in all the algorithms I do, I will keep doing this operation. So it's good to get this in your head because these operations spread over too many pages and you can't see the global picture. So the global picture is always this guy on the top. Okay, so all the operations that I do in the algorithm will always have a W and a V, and they're applied from both sides. And I have to update the A by symmetric transformation, the B by symmetric transformation, and update the P's and the Q's by W and the V's corresponding. All right. The one thing that we will never do, though, is apply W or V directly to T itself. Okay, that's done implicitly. We only need to apply to A, B, P, and Q. Okay, that's the key thing to remember. Okay, now, of course, to invert the Lyapunov-Stein, the Sylvester-Stein operators, you need A and B to be in triangular form. So we need to know their spectral properties already, right? So this is always a major bottleneck in this theory, that you have to have A and B in triangular form. If it is not, you've got to bring it to triangular form cheaply. Okay, luckily for the ones that we talked about so far, for the Topless and the Cauchy and the Van Neumann case, they're already diagonal or lower triangular, so that's not an issue. Okay, but this is something that we'll worry about throughout. Okay, Now the key thing is, of course, we don't have T itself in this way of thinking about it. We only have P, Q, A, and B. And the question is, how can I recover the matrix T from it? Okay, because this is a necessary step in any algorithm that we do, because we need to operate on the entries of T at some point. So here I show a block partition of T where tau is a scalar, S is a column, and T is a column too. So the first row and first column. And I've also broken up A and B. I've assumed that they're lower triangular now. Otherwise, we can't invert operators, right? And I've partitioned P and Q conformly. So little p and little q are just single columns. They're the first row of the right-hand side. Okay, then if you just work through the displacement operator equation, you'll see that you can actually solve for tau, the first column of T and the first row of T through these equations. And of course, for an effective algorithm, you must be able to reconstruct this portion of T, the first row, first column, cheaply. Otherwise, this theory does not give you anything. So this is, of course, just an inner process of O of n flops. Okay, we can live with that. But this involves applying the inverse of a lower triangular matrix, right? Because A itself is a lower triangular matrix. A1 is also lower triangular. Normally, that will cost you n squared operations, in which case this whole thing just falls on its face. So you must have that this is a structured matrix. A1 should be structured, B1 should be structured. For example, A1 and B1 could be Topless matrices. They could be banded matrices. Okay, so the classical theory is mostly concerned when A1 and B1 are bidiagonal matrices, lower bidiagonal matrices, or just diagonal matrices. Okay, those are the classical stuff. Okay, so this is essential, and it will not show up as much in the rest of the stuff that we do. Okay, so what is amazing about the displacement strength structure? Right? We're going very far from what a sane person would do. The key thing, of course, is that if you compute the displacement structure of the inverse of the matrix, it's exactly the same as the displacement structure of the matrix itself. Okay, that's the key thing. The second key property is that if you take a Schur complement of T, it will also have the same displacement rank as T itself. Okay, these are the two key properties that enable displacement rank structure to provide fast algorithms. Okay, of course, it's not all obvious that these two are true. So to prove that the displacement rank of T inverse is the same as of T, you look at this embedding. There are many ways to show this, but this is 2 lines, so it's pretty good. If we take this embedding and you look at the LU and the UL factorizations, you can just read it off from the fact that the ranks have to be the same. So you see that T and T inverse are full rank, so the rank of this block and the rank of that block have to be the same, right? Because everything else is invertible. So those 2 ranks have to be the same. So this shows that both T and T inverse are the same displacement rank. Okay, so the question is, how can I go from the generators of T, which is P and Q, to the generators of T inverse quickly, right? And the answer was known, luckily, before this itself. And the answer is called the Schur algorithm from complex analysis. And that was the initial approach of these methods of Krylath and others, because they came from systems theory where they're already familiar with these things in terms of rational functions, and to then come up with the matrix analog what they did. Okay, so how did they do this? So the way they did it like this is to observe what happens. So they went to Gauss elimination, basically the idea is. Okay, so it's a little bit long route, but I'll go through fairly quickly. The Schur algorithm says how to compute the LU factorization of T if T satisfies the displacement equation. Okay, so here, how do we do Gauss elimination? So the middle matrix is T, right? And I've shown the first row and the first column. And that's the first step of the Gauss transform to eliminate the first row and first column of T. I'm going to eliminate both the column and the row just to keep everything symmetric. Okay, you don't have to, of course. Normally, if you eliminate column, we don't eliminate rows. But here, I'll eliminate both. So if I did eliminate both, I'll get that matrix. And the bottom right corner is called the Schur complement, capital S. And what we are after is to go quickly from the generator for T to the generator for the Schur complement S. So if I can go in n operations from the P and Q, they call the generators of T, to the right-hand side of the displacement equation for S in n flops, in n operations, then I'll have an n squared algorithm for computing the LU factorization of T, which is, of course, much better than n cubed. All right, so that's the idea. Right, so the operations are W inverse and V inverse. So this is W and V that I'm going to pick. Right, these are the elementary Gauss transforms. Then we know I'm going to apply both these from both sides of the displacement equations. I know the coefficients will change like this. So I need to compute both of those. So I go ahead and multiply them. Since they're all lower triangular, you get a lower triangular matrix. You notice that these 2 entries don't change. They're the same as before. So the only thing that changes is the first column of A and the first column of B. And they change by this small operation, which we already assumed that we can multiply by A1 and B1 in linear time. So the assumption is that you can multiply that by linear time still. So you can update A and B quickly in linear time. Okay, otherwise this will not lead to a fast algorithm. All right, so we'll name the new columns B1 and H1, right? And what we are now after is to compute the displacement equation for the Schur complement S, but for that I need to find the massive product up there, which turns out to be this expression over here, right? And I go through and multiply it, and I get a part of the thing. Here's the displacement term, the second term of the displacement operation for S, but I have this rank 1 thing sitting over there. So the question is, what do I do with the rank 1 thing? Right? I also need to apply W inverse to the generators P and Q on the right hand side. So I go ahead and do that, and that is, you don't care. It's always going to be take you linear operations, because P and Q are very narrow matrices. For the Topless case, there are only 2 columns here, and there are 2 columns over there. So it's very small operations. So they don't count for anything. Okay. Now here's the critical claim. The claim is that if you keep just the lower part of A and the lower part of B and form the displacement equation for the Schur complement S, you'll have exactly the same displacement rank as for the original matrix T that you started with. Right? This is the claim that we're making. So we go back and we mangle this equation. We just have to take this term to the right hand side and discard the first row and first column of the displacement equation. You'll see that on the right hand side for the Schur complement, it's P2 Q2 transpose plus this extra term, and you churn through some algebra, and you can see that it'll always factors like this, right? So if alpha and beta, what are alpha and beta? Alpha and beta are the 1, 1 entries of A and B of the lower triangular parts. So if alpha and beta are non-zero, this directly shows that the Schur complement has the same displacement rank. However, if alpha and beta are not zero, this formula obviously is false, and alpha and beta are both zero when T is a Topless matrix. So we want to deal with that case. You can show, again, by backing up to the previous equation, that if alpha and beta are zero, then P2 Q2 transpose will have rank at least 1 less than the one that you started with. Okay, so therefore adding 1 more rank does not change the overall rank. However, this loss of rank is a pain numerically, right? Because to get a loss of rank means some precise cancellation had to happen. So the original set of Schur algorithms would become unstable at this point, but eventually this was fixed. Okay, we figured out how to take care of this loss of rank properly. So now there are stable versions of the Schur algorithm. Okay, so this is essentially does it. So you now form the Schur complement. It has the same displacement rank. You know the generators for it. You can repeat again, and you keep doing this again and again and again. Every step of the Schur algorithm will generate 1 column and 1 row of the LU factors of T. So in n-squared operations, you can compute the LU factorization. The assumption was that both A and the coefficient B are lower triangular. You can multiply by them in linear operations or something close to that, and you can invert them and apply them to X also in linear or something close to that. Right? As long as you can do this, you will have a fast algorithm, and therefore this is the Schur algorithm. Okay, and this was the first time it was through this technique that you produced the first stable fast algorithm for applying the inverse of a Topless matrix to a column vector. Okay, so just to summarize, the Schur algorithm is in general unstable, right? Why? Because we're doing LU factorization without pivoting. So you're going to get the same growth factors as if you don't pivot. So it's in general going to be a terrible idea, right? However, there are some special cases, and these have been exploited recently in the last decade or so to make these algorithms stable. The first is if A and B are diagonal matrices, then you can do pivoting from both sides and preserve the displacement structure. A and B will remain diagonal. Since you can pivot, you can do either partial pivoting or complete pivoting as you want. And both Mingu and Vadim Olszewski show that you can do pivoting and keep the O of n squared complex with the Schur algorithm. So for Cauchy matrices in particular, this means that you can compute the LU factor of the Cauchy matrix in n squared operations with pivoting, and that was completely numerically stable. All right. The next good news is that with some little bit of work, you can take the traditional Schur algorithm and also stabilize it by doing some things carefully. Okay, so you can also stick with the general with the traditional Schur algorithm, but there are some. It's kind of a mess to show how to stabilize this. I'm going to skip over it over here, especially since I know that most of you don't care about numerical stability. But it just means you can keep the numbers from going too far. You don't have to use too many bits to store all the intermediate computations. Okay. However, the big drawback of the Schur algorithm is that the computed L and U are completely unstructured. Okay, at least the way I presented it, I did not try to capture any structure in the L and U. So after the LU factorization is done, you have a generic L, a generic U, and you cannot do anything faster with those two algorithms after that. Okay, which is a problem. So these were all fixed eventually. So I'm going to talk about some of these things. Okay, the first thing is that the displacement structure is the first one that you come across is not necessarily the best one. For example, Topless matrices are used to downshift matrix, right? And then I said, okay, we can't do pivoting on this. We'll do some funny stuff. But people realize, oh, that's easy to fix. Okay? So the idea is you take the downshift matrix and you do a rank 1 perturbation on it. Okay? In this particular case, I added a phi to the top right corner. If I take phi to be 1, I, of course, get the circular shift matrix. Unfortunately, in the displacement operator, if I pick A and B to be circular shift matrices, I still get a low rank right-hand side, but the operator is no longer invertible, right? And we need the operator to be invertible to specify the matrix T properly, so that is out. So normally, conventionally, people pick that phi to be a number slightly smaller than 1 or like 1/2 or something like that, okay? So you pick some number phi. It doesn't have to be 1. It can be something else. Okay, you don't want it to be pick it to be 1. And the good thing is that if I pick Z phi, I can still compute the eigendecomposition of Z phi in terms of the FFTs. Therefore, by applying FFTs to the P and Q, I can convert a Topless matrix to a Cauchy matrix, right? Because once A and B become diagonal, the matrix is called a generalized Cauchy matrix, becomes a Cauchy matrix at the cost of 1 FFT, which is n log n operations. And then once I have a Cauchy matrix, I can compute its LU factorization in n squared operations, a completely numerically stable one. Okay? So in practice, for reasonable size problems, that is still the best approach to go going forward. Okay? You can go from n squared to n log n by using further ideas that we'll talk about at the end of this tutorial, but that will only kick in when the matrix becomes reasonably large. Okay? So this is a good technique otherwise. All right. Now, there are a couple of other things that are good to know, because I said like this is a grab bag of techniques, displacement structures, so it's good to know things. So I said, for example, for certain choice of A and B, the operator, the Stein operator might be non-invertible. For example, for the standard Cauchy matrix, the operator is not invertible. So usually you have to do some little bit of algebraic manipulation to make it invertible. The simplest one, of course, is pick one of A or B and do a rank 1 perturbation on it. By doing a rank 1 perturbation on it, you don't change the eigenstructure too much, and hopefully you can compute the new eigenstructures quickly and still make them applicable fast, which is the technique that I did in the previous slide. In general, it's good to notice this general observation. If A is a symmetric matrix and I do a rank 1 symmetric update to it, so if I say, let's say A is a diagonal matrix, right, which is what happens in the Cauchy case, for example, but the operator is not invertible. So what I want to do, I want to perturb one of the eigenvalues, either of A or of B. I pick A. A is diagonal. I add a rank 1 matrix XX transpose to it, right? Now I have to diagonalize this guy. When we diagonalize this guy, there's one good thing to keep in mind, that the eigenvectors of the symmetric matrix A plus XX transpose are themselves a Cauchy matrix. Okay, so Cauchy matrix is actually has orthogonal columns. So you can apply this matrix quickly to another vector. The techniques are again break into 2 classes. If you want an exact application, you have to go back to some polynomial arithmetic, which is not so fun. If you want an inexact application but high accuracy, then you can do it by technique I'm going to talk about later on in this tutorial. Right? But it can be done. But again, it starts getting messy. Okay, so this is like like this big crank you have to turn by fiddling with these things. And Victor Pan, I'm not sure if he's here or not, has written a lot of papers connecting all these different classes together using FFTs, Cauchy matrices, and so on. So there are a lot of things talking about how to go from one structure to the other using these ideas. I'm not going to say too much about it here because I would like to start wrapping up displacement structure now. So the last thing, notice what I said, when we do the Schur algorithm on the T matrix, it produces unstructured L and U. So if we try to compute T inverse from the from the L and U factors, it will produce an unstructured A inverse, right? So that's not good. So there's a simple technique to fix this. If I look at this 2x2 embedding of the matrix T, right, and if I compute the Schur complement of the bottom right 0, you see it's T inverse. All right, so the T inverse is a Schur complement of that matrix over there. So if that matrix had a displacement structure, I could use the Schur algorithm to find the generators of T inverse in n squared operations. All right, so the only question is, how do I find a displacement structure for that matrix over there? Right, and you can come up with some conjectures. So here's one I wrote down. So I said, okay, let me guess that that should be the A and the B for this bigger matrix. I took the A and B from T, and I used the pseudo inverses over here and there. And you can then show that the rank of this matrix, of this displacement structure, is at most the original displacement rank of T plus the rank of this orthogonal predictor and the rank of this orthogonal predictor. So if things are good, these 2 ranks will be small. Like in the case of the Topless matrix, this is at most 1, this is at most 1, right? So which tells you that you can actually find a good displacement rank for this bigger matrix, and therefore you can use a Schur algorithm to find the generators of T inverse. And if you can find the generators of T inverse, then if you write the displacement operator in a slightly different way, you get the famous Goldberg-Semenkel formulas for T inverse. Right? The Goldberg-Semenkel formula just says that T inverse can be written as a product of a lower triangular Topless, upper triangular Topless, plus lower triangular Topless, upper triangular Topless. So T inverse is not Topless, but it's the sum of the products of 4 Topless matrices. Right? And that just is another way of stating the same displacement equation again. Okay, so I don't have time to talk about that, but that's possible. So in principle, you can find the generators for T inverse in n squared operations. So therefore, though T is not Topless in the Topless, T inverse is not Topless in the Topless case, it still has displacement rank 2. And you can find them in reasonable time. Right? Now, there are a few other operations you would like to talk about with displacement structure. For example, if T1 and T2 are 2 displacement structured matrices with coefficients A1, B1, A2, B2, what about the product? Again, it's not as nice as you would want, so there's one result that is known. If I take A1 and B2 and form the displacement structure of T1, T2, then the rank of that is no more than the sums of these two ranks, which is not bad, plus this one yucky term, which is B1 transpose A2. Well, this is not too bad. It says if you multiply 2 Topless matrices, you won't get another Topless matrix, but you get a displacement structured matrix with slightly higher rank 4 or something like that. I think 5 maybe. Okay. What about Cauchy-like matrices? Well, in general, that will not be low rank. So for 2 arbitrary Cauchy matrices, if you multiply this way, we don't know what the displacement structure is. But if you take 2 special Cauchy matrices, where B1 transpose A2 is essentially identity, then you can show that it will still be Cauchy-like. Right? But I would say that much of this thing is very ad hoc right now. Okay, I mean, we don't have a clear answer. There might be a better way of doing this stuff. Right? There are papers about this. You can look it up. Okay, so what about the open questions? Well, there are plenty of open questions. You can see my whole presentation was sort of like very, not so good. Okay, so what is the thing? Well, the first question is that, if I give you a family of matrices T, how do I pick A and B to get good displacement structure? Okay, so this question is completely open. Usually people have already guessed, oh, for Topless we should pick A and B like this, for Cauchy we should pick like this. But if you give you some arbitrary class and ask you, does it have good displacement structure, nobody knows how to answer it. Okay, so that's pretty bad. The converse is also surprisingly open in many cases. If A and B are lower triangular Topless matrices, what does this T look like? Right? I mean, can I identify it in the wild? I don't know. Right? So that's also, we don't know anything about that. The surprising question is that displacement structure is very good for applying T inverse quickly to X. However, it remains strangely silent about multiplying T times X. A lot is known in special case. There are lots of papers saying, okay, if A looks like this, B looks like this, we can do. But in general, there is no theory that matches T inverse times X. Okay, so just because you can apply T inverse X times quickly doesn't mean you can multiply T times X quickly, which is very surprising. Right, so that's I think is worth looking at. And finally, of course, where it really falls flat in practice is that if I look at sums of tensor products, then we don't know what to do. Right, so for Topless block Topless matrices, for example, the displacement structure does not improve the state of the art at all. So these are all open questions. Okay, so that was displacement structure. So it did good for one-dimensional problems, as an engineer would say, but for high-dimensional problems, it did not do so good. So people then went on to other things. So what I'm going to talk now about is structures where we exploit low rank much more explicitly and much more symmetrically and simply, in my opinion. Okay, and it has the nice power that it actually takes care of all the structures that we looked at so far too. Okay, so how do we use low rank? Okay, low ranks are very simple things to use. That's what's nice about it, unlike displacement structure or polynomial structure. So because A can be written as product of 2 low rank matrices P and Q. So P is a skinny matrix with R columns, and Q is all the same thing. Right? Then to multiply A times X, we well know that you should reorder the multiplication as Q transpose X first and then multiply by P. And you can reduce the number of operations from n squared to n times R. Right? So multiplying by a low rank matrix is very easy as long as you just move the parentheses around. All right. Furthermore, if I give you the matrix A and I tell you it's got low rank, you can find P and Q in a reasonable amount of time. Just Gauss elimination will do it. And you must be on the lookout for 0 rows and columns during Gauss elimination. So you can do it in n squared operation, right? Which means it's essentially linear in the number of entries in the matrix A. So that's good too. So it's very trivial. I mean, there's nothing much to do. All right. The next thing is inverse. Of course, we can't invert a low rank matrix, but we can invert I plus PQ transpose in general. And we know the famous formula for applying that guy. And that guy shows that formula shows that, yes, you can apply the inverse also in linear time. Right? Again, by the same trick name, because this is also low rank. this odd by odd matrix over here, so that takes only r square operations to apply. R cubed operations invert. R is considered small compared to n, so the whole thing can be applied in n r squared operations, right? So this is it. So everything we do is low rank in the rinse and repeat of these ideas, just in some nested, complicated fashions. Okay, so that's it. So if you can follow those two, the rest of it is just, yeah. Okay, now because the structures, the low rank structures we're going to use are fairly involved and the algebra is kind of complicated, I'm going to give you some big picture view of, in hindsight, we wish we had done the original papers this way, so I'm going to present it that way. And I should also add that I don't think that the way I'm presenting the tutorial is the right way to think about this problem necessarily, but it's a good way to sort of look back in the past and say, okay, this is how we could have done it. I think there are even better ways right now to do it, but I'll do it. I'll try to reflect the papers as much as I can. Okay, so the idea is that when you work with low-rank matrices, basically you're talking about sparse matrices. Okay, these turn out to be identical things. All right, and this equivalence is very important. So as long as you understand that you're working with sparse matrices, almost every algorithm becomes trivial. All right, so what is so for example, if I take a banded matrix, bandwidth k, Gauss elimination on that, there is a bandwidth aware. I didn't know there are only k bands, will take only n k squared operations. So Gauss elimination of banded matrix is only linear operations, right? However, Gauss elimination is a finicky beast. If you give you an arbitrary sparse matrix and you don't reorder it correctly, the cost can fluctuate quite a bit, right? For example, this is an arrowhead matrix. So I'll use this club suit to denote non-zeros, whose numbers I don't care about. Okay, so this is just a way to denote the structure, so you don't get distracted by numbers sitting there. So this is called an arrowhead matrix, like that. So only the main diagonal, last column, and last row are non-zero, potentially non-zero. Everything else is definitely zero, right? If you do Gauss elimination in this ordering, right, so use this number to eliminate this, and this, you see that you get no fill-ins at all. You can do Gauss elimination on this in linear time. However, if by mistake you reverse this matrix and you take an arrowhead like that, then you see the very first step of Gauss elimination will start filling in the second row and the third and so on. So after you eliminate the first one, you have a completely dense matrix, right? So if you do Gauss elimination in the wrong order, you can take a linear time algorithm and make it n-cubed algorithm. So when you're working with sparse Gauss elimination, the key thing is this ordering, and it is well known in computer science that finding optimal ordering is in general NP complete or NP-hard or something like that. Okay, so you can't delegate this task to the program. The human has to sit there and figure out what is a good ordering first. Okay, so for most fast algorithms in this half of the talk, it's effectively I'm solving this combinatorial problem. I'm saying, okay, I can convert this problem to this sparse matrix problem, and for this sparse matrix problem, I need to find a good ordering of the rows and columns for Gauss elimination. Okay, so that's the flavor of the thing. All right. So remember, I need to convert these low-rank structures to sparse matrices, right, for this connection to work. Okay, so I'm going to specify how that is done. All right, so let's look at this baby problem. I want to apply a diagonal plus low rank inverse to x. Right, so this is my prototypical low rank problem. Okay, this is the canonical example of what I'm going to do. So how will I do it, right? So the philosophy I'm propagating is this: don't attack it directly. I know I'm for all of you this is a very trivial problem, but break it out into steps. First, ask the simpler question: how do I multiply by d plus pq transpose times x? Okay, forget about the inverse. How do I multiply first, right? If I'm going to multiply, here are the intermediate stages I would do. I would definitely want to multiply by q transpose x first. I call it y. Then once I have y, I can form the right-hand side be the product as dx plus p1. Okay, and each step, of course, takes only linear time. That's the key thing. And these intermediate variables capture the state of the operation. Okay, so this is called the Statespace Approach in engineering. All right. So if I write these two equations out in matrix form, this is what it looks like, right? So this thing captures exactly those operations over there, right? And notice that this matrix is a very sparse matrix, right? This is skinny. This looks like a block arrowhead matrix that I talked about before. That's the idea. Okay, so that matrix up there is equivalent to this arrowhead matrix, graphically speaking. Okay, so I can reduce operation over there to operation involving the sparse matrix instead. So multiplication means multiplication by the sparse matrix, or in this case solving, right? I need to find b, so I just multiply by this guy. All right. So now my goal is given b, I want to find x, right? If I'm given b, I want to find x, I want to apply the inverse. But notice that the same equation applies again, right? Of course, along the way, I have to find y, but that's fine, right? And this is a nice square matrix, so I can ask, is this invertible, and so on and so forth. And of course, I can do this. So notice that if I do Gauss elimination in the wrong order on this, so if I eliminate y from this equation first, I get the Schur complement of this block, which is what I started with, d plus pq transpose. In other words, that structured matrix is just the Schur complement of this sparse matrix, right? And when we do it this way, these are called the diagonal representations of the matrix. Okay, so this is damn good. Okay, so the key thing is convert this dense matrix as a Schur complement of a nice sparse matrix. Observe that for this sparse matrix, if I eliminate in a different order, right? If I eliminate downwards instead, then I can compute the LU pattern of this guy in linear plots, and I can find x and y. So that's what I did up there. I did Gauss elimination, eliminated a 0 over there. I got one step, found y, right? Found x after that by back substitution, plug it all back in, and I get the famous Sherman-Morrison-Woodbury lemma. All right, and this, of course, is a linear time operation for that operator. Notice that even if I don't realize I can work out the operations by hand, I don't care, right? I can just stop here, give this to my sparse matrix software package, and it will find it in linear time for you. You don't have to worry about the ordering. As long as the user using Metis, for example, to do the ordering, it might find a good ordering, or do it by hand, like in this case. All right, okay, that's the philosophy, and this is what I'm going to rinse and repeat now. Okay, so first we're going to start with what is called the sequential semicircular representation. These were unfortunate nomenclature choices by me. My graduate student walked by one and said, we have two of these, what should I call each? I said, well, let's call one sequentially.
May I interrupt? So it's been an hour, so I guess we may take a very short break of maybe.
Okay, good time.
5 minutes. 5.
Cool.
2 minutes doesn't, so since it's like
yeah.
a next section, maybe we can have a round of questions on this very first question.
Or a bathroom break?
Talking about the ordering for Gaussian elimination, that it's NP-hard problem to determine the optimal ordering.
Complete hard for general sparse matrices, yes.
Is it? I don't know what the reduction is. Is there any approximation algorithm? Like in this case, you would be quite happy to have a factor 2 approximation of the optimal ordering.
I don't know. That's a good question, actually. I have no idea. I have not thought about it along those directions.
I mean, they do it. They do graph separators and all that.
Right. There are all of those heuristics, but they
don't do this.
Right.
But are those just heuristics, or are they?
No, they're theorems.
Some cases they have theorems, but it depends upon. I mean, in some cases. So let me put it this way: for the graphics that arise in my field, we know of no good orderings for them. So the ordering that we know, we can theoretically say they have this complexity and they're not very good. So unfortunately, I think that. Oh, my students have tried it, yeah. So I'll talk about it a little bit later on, yeah.
Okay.
Yeah.
Do we have any other question on this first talk?
Question?
You mentioned divide and conquer several times.
Yeah.
In the first few talk. Can you point us to kind of one of the original papers that discusses that approach?
Okay, so just for Strassen, you mean? Or for?
Just in general, divide and conquer approaches to decompose.
I'm not sure whether people, okay, so definitely this is distributed across the literature, especially for Strassen's paper, definitely talks about divide and conquer for the fast matrix multiply. FFT, of course, uses it. I think there are something called doubling algorithm for the Schur method, which, I only talk about n-squared algorithm. There are also n-log, which also use something called the doubling algorithms. So any paper on doubling algorithms for displacement structure will talk about how to use that for special cases of the displacement structure. The fast multipole method literature uses divide and conquer all the time. Question?
So quite a while back, you had like a padding on a Topless matrix. It was very early on. So with analogous to padding, there's also a peeling Straussian, I believe. I was just wondering if that appears at all. If you receive any like non-binary size matrices, use peeling and padding, or is that not useful?
For Strassen?
Yeah.
Oh, for Strassen, you have to pad too.
Sorry?
For Strassen, you don't have to pad. I mean, it depends upon the size. You could pad. He's saying no.
You can also peel.
Oh, you asked, oh, yeah, sorry. You can peel too, yes. That was the question. I missed the peeling part, yeah. I was just trying to give one way to do it, yeah.
Sorry. So you showed us the Schur algorithm stopped in the middle to compute the generators on the inverse of the matrix.
approaches?
Yeah.
Is that what's currently done?
Oh, I think the method I present is numerically unstable. Yeah, I'm not sure whether there are really good techniques, numerically stable techniques for getting at the generators for the inverse. Because all the other techniques, apply some transformations, so then you have these other things you have to unwind to. It's probably unwindable, so maybe convert it to Cauchy if I'm generators there, then unwind the FFTs again. It's probably the right way to do it if you want to do it numerically stably, yeah.
I guess there's no more questions. We may resume. Let me just check and make an announcement.
Okay. Should we start again, or?
Let's start again.
Okay, are we ready to go again? I'm not sure who is harder on, the person who's listening for 2 hours or the person who's talking for 2 hours. Okay. Okay, so now I'm going to go on to the class of algorithms that have had, I guess, a lot of impact in engineering practice. We'll start with the fairly simple one. Okay, so this is historically the earliest one. These are called the sequentially semi-separable representations. And this is one way to exploit low-rank structure in a matrix. Okay, and it's maybe the simplest one to talk about. So the idea is like this. Okay, so the initial idea is fairly simple, but let me try to say. So let's say again we have a square matrix A, right? And I partition it into 2 by 2 blocks such that the diagonal blocks are still square. Okay, so I put a club suit over there to say I don't care about them, and we don't care about the diagonal blocks in this way of thinking about things, right? So you see there are 2 off-diagonal blocks, A01 and A10, and they don't cross. They don't have any diagonal entries on those 2 blocks. So we're going to give them names. So these are called Henkel blocks because of some people who only did this from systems theory. So the top block I call H_M. M means I skipped M columns to get to that block. And G_M means it's the Henkel block and the lower triangular part, and I skipped M rows to get to it. Okay. Now, what the sequential semi-separable representation tries to exploit, and this is just one way of thinking about the problem. Okay, it's not necessarily the best way, is that it tries to exploit the fact that A01 and A10 might have low rank, right? And not only just this one Henkel block, but all the Henkel blocks for all M from 1 through n-1 might have low rank. It tries to simultaneously exploit the lower rank of all of these blocks, right? So the increase in complexity now is just that you have all these overlapping Henkel blocks, and you're trying to exploit all the low ranks at the same time. Okay, so for example, H1 is that Henkel block on the top, H5 is this one. You see they both overlap. We're assuming that they're both low rank, and we want to exploit all of these Henkel blocks, right? H1, H2, H3, all of them have low rank. We want to exploit similarly for the lower Henkel block, the G, the bottom part. We want to exploit the low rank of all of these Henkel blocks, and we want to exploit it for both matrix vector multiply, matrix inverse times X, matrix times matrix, all of that. Okay, so that's what we're going to do. Right. So once you get this idea, the rest of it is just elbow grease, in my opinion. Okay, so once you this is the Henkel, these are the ranks you have to exploit, then it's fairly routine work. Okay, so you say, okay, I need to come up with a way to represent the matrix A. Okay, I need to come up with numbers that I'm going to use such that I can pick those numbers freely. And let's say, for example, all the Henkel blocks have rank at most 5. Then I pick some numbers such that if I generate the matrix using those numbers, I'm guaranteed that all Henkel blocks will have rank less than 5. Right, and should be a representation. And then once I have found the representation, then hopefully the rest of the algebra will just be simple stuff. Right. So the key thing is to first find a way to represent this matrix such that I capture the rank of all the Henkel block H1 through H5 and all the G's at the bottom. Okay, so all of these Henkel blocks, all the A01s, A10s, all their ranks should be captured. Once I find out how to represent it, then I'm done. Okay, and it's very simple, and it's just thing. Okay, so here's the representation. Okay, so here's the matrix A. Okay, and I know all these Henkel blocks have low rank. let's say the rank is at most R. So now what I'm going to do is I'm going to find these matrices D, I, P, I, Q, I, R, I, U, I, V, I, all these 7 guys. None of them are bigger than R by R, okay, such that if I pick those numbers freely, I'm guaranteed that all the Hankel blocks will have rank at most 5, or R in this case. And conversely too, if this matrix has Hankel blocks of rank at most R, I can find D's, U's, V's, P's, Q's, R. This is true, okay? So this is represents in some sense the right way to think about the matrix, okay? That's the key thing. Okay, notice this weird pattern in these matrices, but it turns out it's actually just a chimera. It's not the right way to think about this problem, and I'll show you a little bit what is the right way to think about the problem, but it's fairly easy. So I carefully picked the indexing so that you can see that the number is always running at 0, 1, 2, 3, like that. Right? The lower triangle, but I go backwards. But other than that, it's a fairly thing. The R's will always appear on the inside, the W's will always appear on the inside, and the D's are the diagonal entries, and we don't care about those. Okay? So this is called the sequential semicircle representation, and so you can see the representation is nonlinear, but the basic problem we're trying to solve is nonlinear, so it's going to look like that. So what is special about this representation? Again, for people who use the systems theory, this is obvious. Okay, so if I look at one of the Hankel blocks, right? So if the Hankel block, remember, is one of these blocks like that. So if I take one of these chunks of this matrix, it'll always factor out into a column and a row with exactly R columns and R rows. Okay, so there will be R columns here because this guy has only R columns and that guy only has R rows. So it'll always factor out like this. Okay, that's the key thing. So the fact that this representation has Hankel rank at most R, is sort of SSS rank R, is trivial because of this product form. Okay, and this product form also tells you how to compute the representation. Okay, this is, you have to stare a little bit. It's not what you think it is sometimes. Your first guess for computing this is usually wrong for most people. At least for me, it was wrong. Okay, so what this tells you is that you have to sort of do this recursively. Okay, so if I look at H1, so I look at the first Hankel block, that one, H1, then the first Hankel block, if I look at this factorization, it will have U1 and nothing above it, right? So it tells me that U1, for example, is the column basis of H1. All right, so that's what it tells me. Okay, and then when I look at the second Hankel block, H2, it will have U1, W0, U2, like that over here. So it tells me what this part is and it tells me what the W is. Okay, I have to reuse the column basis from the previous Hankel block to generate the column basis for the next Hankel block. And that tells me what the product W is and then what the new U that's coming underneath is. Okay, so you have to generate the column and the row basis using this special structural constraint. And once you see that this is a recursive procedure, then you can show that in n-squared operations, you can convert a dense matrix, any dense matrix, whether it's low rank or not, into the sequential semicircle representation like this. Of course, if your dense matrix had low rank in the Hankel blocks and the off-diagonal blocks, then you will get very parsimonious representation of the matrix. All right, so I won't say more about it because it's just simple stuff, right? So you can construct from this formula the U's, V's, W's for the upper triangular part, and simply by looking at the lower triangular part, do the same thing on the transpose. You can compute everything in one sweep, and n-squared R operations. R is the rank of these off-diagonal blocks. Okay, this is the low rank part of this matrix. All right. In special cases, you can construct this representation faster than this. Okay, for example, one special case would be if the matrix was a banded matrix. For example, here it's a tridiagonal matrix. In this case, you can just stare at the matrix and write it down. Okay, you can see that the diagonal entries should just be the diagonal entries. You can take Ui, for example, to be the upper diagonal entries. The translation operators can be zeros and ones, and this, right? You can just plug it all back in and check that this is SSS. This tells you that the SSS rank of a tridiagonal matrix is 1, right? Because if you take any Hankel block, it has most one non-zero in the bottom left corner for the upper Hankel blocks, and most one non-zero in the top right corner for the lower Hankel blocks. So the rank's always 1, and this tells you can write it like that. Okay, right, this is the canonical example, the tridiagonal case. All right, so now that we have the representation, what can we do with it? Well, the philosophy, this will consistently follow this philosophy. Always do matrix vector multiply first, take matrix vector multiply, write it as in sparse matrix form, come up with a good ordering for the sparse matrix form, you'll get a good algorithm for T inverse times X, then wring your hands to find LU, QR, and so on. Okay, so that's the protocol thing. So here's the matrix. You want to multiply with this X vector to give me that vector. right? If you stare at this, so just consider the upper triangular part. The lower triangular part is dual to that, so it's easy. You see that every term in the upper triangular part starts off with a v, so you must multiply v times x somewhere, right? You cannot avoid it, so you just go ahead and do it, right? So we call each of the v times x's. So v1 times x1 is g1, v1 times x2 is g2. Okay, so this takes p square r square operations. So just go ahead and do it, right? Then we notice that so all of these things have been done. Okay, so next we notice we go back to the Hankel block factorization. You have to multiply by this Hankel block eventually, right? So this Hankel block, we have to multiply the x sitting over here eventually. That has to happen. All right, so you dig in a little bit, and you see that, okay, I'm going to multiply by this row times the corresponding x, the column that you're trying to multiply eventually. But you see that this thing looks suspiciously like a polynomial multiplication, so Horner's rule must apply. Right? So therefore, we see that there must be a factored form of this possible. So you see in particular that, you know, if you look at terms to the right, they have common terms, right? All of these are common as you go to the right. So therefore, right, we just have to apply Horner's rule, and you stare at it a little bit, and you see that all you have to do is to take the term to your right, multiply by wj, add it to vj transpose x, and you get the product up to the inside for this term over here. Okay, so this is gj plus 1, vj times added, you get the gj for this. Okay, so that's the intermediate calculation. It's called the gj. This is the state space variable for this calculation. All right, anyways, this should be easy for you. So you have to compute this term no matter what, because that's the factorization in the Hankel block on the upper right? So these calculations are computed. Notice this is a left-going recursion. You need to find gn first, and then you go to the left, gn minus 1, gn minus 2, like that. I'll show you a state flow diagram for this. Okay, so there's exactly similar calculation for the lower triangular part with the q zeros, but it goes to the right and it looks like that. It's a mirror image of that. So once you've formed all of those, then you can write down the final output, right? If you look at it over here, right, you need to multiply this u times the incoming g and send it out. So that's exactly what's being done over here. The u multiplied with the g, same thing from the left, and then the diagonal term. This is 3 operations, right? And if you look at it very carefully, you notice that if you never multiply by more than an r by r matrix at any stage, there are a finite number of them, at most n such terms. So the whole algorithm costs n r operations in general. Okay, so this is the way to multiply a matrix in SSS form times a vector fast. Right? And it will be fast if the rank is slow, it will be slow if the rank is high. That's it. Right? So now that gives you the fast matrix vector multiply. Notice it was quite trivial. Okay, there's no funny divide and conquer stuff. So just Horner's rule applied basically. Okay, so now we write the whole thing in sparse matrix form. Okay, to write it in sparse matrix form, I put all my w's. So remember, the w's are the matrices that appear inside the upper part over there, right, in a diagonal. Right, I take all these g's that I'm computing, the state space variables, and I put in a column over there, little g. Right, I do the same for the other guys. So I take all the u's, put in a diagonal matrix. I take all the v's, put in a diagonal matrix. I take all the p's, all the q's, all the r's. Everything goes into a diagonal matrix, or block diagonal matrix. Same thing for the h's, all go into diagonal matrix. Okay, and then you make this very nice observation that if I look at just the recursion for computing the g's, I can write it in diagonal form like this. Okay, it is g. This downshift says, okay, move the g over one bit, multiply by the w, add it to v transpose x to give me the g. Okay, so these two recursions over here, right, gj depends upon gj plus multiplied by wj plus this is written in this nice form as this identity minus, this is a bidiagonal matrix times g is equal to v transpose x. Right? Of course, in this way of writing it, it looks non-causal. To compute g, you have to apply the inverse of that bidiagonal matrix to v transpose x. Right, but that's just forward substitution, or back substitution in this case. It's upper triangular. Okay, similarly for the lower triangular part, you have this recursion, and you can rewrite that recursion as identity minus diagonal of all these r's. The downshift matrix times h is equal to q transpose x. Right? The key thing is that I encode the multiplication recursions as diagonal matrices, or closer, in this case bidiagonal. Right? And then finally, the last one, this thing can also be written in matrix form as this expression, this is diagonal, diagonal, diagonal. All right? And you notice that again the downshift matrix plays a role because there's a recursion going on. All right. So what we really want to do, of course, is to go backwards. We want to say that, okay, I'm given B, so given B, find X, assuming you already have the SSS representation of the matrix. That's what we really want to do. And our philosophy is that to do that, you take the multiply recursions, write them in a sparse matrix form, and there's the sparse matrix form. So I've combined this, and this equation into a single equation up there. Okay, I've just rewritten it. And I put all the X, G, and H together over there. And that's the recursion. And notice again this famous arrowhead matrix comes up again. Okay, notice that it's important to observe the sparsity pattern of the sparse matrix, because then it tells me how to reorder it. All right. So in this case, we first do the bad ordering to get the diagonal representation of the original dense matrix. And you notice that if I eliminate G and H from this equation by Gauss elimination, I get an equation for X and B, and that must be my original matrix. So I go ahead and do that. I eliminate G and H. You can see since it's arrowhead, you have to find the Schur complement of the 1, 1 block. You can do this in your head. And I get this representation over here. Right? Which tells me that this matrix A in SSS form is just this expression involving diagonal matrices and the downshift matrix. So in other words, this horribly complicated dense matrix is just a Schur complement of some large sparse matrix. Right? And that greatly eases further calculations. All right. Is okay? And not only that, this form also tells you directly how to multiply A times X quickly, right? Because multiplying A times X, multiply from this side, this is a diagonal matrix, easy to do. You need, this is a lower bidiagonal matrix, so we do back substitution. Diagonal matrix, easy to do. Diagonal matrix, easy to do. Upper bidiagonal matrix, back substitution with the bidiagonal matrix, easy to do, so on. So it encodes the fast multiply, even if you do not know anything about it. As long as your software knows it's a sparse matrix, it will do the right thing for you. All right. So this is called a diagonal representation of this matrix A, right? And notice that it splits into diagonal, strictly upper triangular, and strictly lower triangular parts. Okay, that's how it splits. So those are the three terms it has. Okay. So the key thing is that how does this tie with the original representation that we wrote down, which is what most people write down this one. And the key thing is to notice this. We need to find the only messy terms are these two inverses, but they're very easy to write down because they're both bidiagonal matrices. So for example, if I look at I minus WZ transpose inverse, it looks like that. It's a bidiagonal matrix. It's trivial to see that that inverse looks like that, and that's where those messy products come from. It's just the inverse of this bidiagonal matrix. Okay, that's it. Okay, so now we want to apply the inverse. So we know that if we keep this ordering and eliminate G and H, we'll get into trouble. Okay, so we need to find a better ordering of this matrix. Okay, there are a couple of ways to think about it. I'll just tell you the answer, then I'll talk about it later on. So it turns out that the right ordering is to perfect shuffle X, G, and H. So you have XI, GI, HI together, clump them like that. If you shuffle them like this into this ordering and do the same thing on the equations as you do on the rows, then you can notice that I can rewrite those equations like this instead. Right? So this is merge 3 variables into 1, and then I rewrite the equation. Each equation looks like this. So in other words, the ith variable only talks to the previous one and the next one. So it's a block tridiagonal matrix in this reordering. And of course, we know for block tridiagonal, you can even do QR factorization with that fill-in, roughly. Right? So it's a numerically stable method to find the inverse. A better way to think about this actually is to just forget about all this stuff. Look at the graph directly. Okay. So if you look at matrix vector product, there's a signal flow graph for that. It says that, okay, I'm given X, I need to find the output B, right? So for example, the diagonal terms multiply X2 to give B2 like that and so on. So that's the signal flow graph of that. The X's also take part in this back recursion. For example, I knew that if I multiply X5 by Y5, I get G5. Then I multiply X4 by V4, add G5 times W4 to get G4 like that. Okay, so this is a signal flow graph of the computation. Okay, this is how an electrical engineer would think about it. Right, this is the signal flow graph. The signal flow graph is actually cleaner to understand what's going on, right? So you see that given X, I follow all the outputs to the outputs B, right? And the multipliers are sitting on the edges. Now, of course, we want to go backwards, right? We're saying given X, I want to find B. So given X, I want to find B because I don't know any of the G's or the H's either, right? But notice that this graph is also the sparsity graph of those equations. So since this is also the graph of the sparse matrix, you see I just need to come up with an ordering of this graph which has no fill-in. But we know that the linear graph has no fill-in. Right? So you can just reorder this into a linear graph. That's easy to do. Put these unknowns together, these three unknowns together, these three unknowns together, these three unknowns. Then this graph becomes the same as a linear graph. And then we have no problem factoring that graph. So you can also think of the SSS representation as a representation corresponding to a linear graph. Right? Of course, then graphs, what about other graphs? So there's a separate talk about that. But in this talk, I'll only cover two graphs, this one and a perfect binary tree. Okay, so next we want to add two SSS matrices, but that's trivial to do, add or subtract. So you see that all you have to observe is that if I look at, say, two of the Hankel blocks on the upper part for each, the Hankel blocks just add up, so the SSS ranks are just going to add up. So question is, given the SSS representation of A and given the SSS representation of B, how to find the SSS representation of A plus B? Because the representation is nonlinear, even for addition you have to apply some work to find the representation. Fortunately, for this class of problems alone, we can do it by some elegant techniques. Okay, so this was first invented by, as far as I know, by systems theorists, but I also heard that there's some people in operator theory who knew about this approach. Okay? So I'm not sure about the history. But anyway, I learned it from Patrick DeWolder. So the idea is that just look at the strictly upper triangular part of the first matrix, strictly upper triangular part of the second matrix, and we know in diagonal form it looks like that. And the question is, if I add two of these forms together, can I rewrite it as a single term that looks like this? So diagonal, lower bidiagonal, upper bidiagonal inverse times this. Okay, so you just bring it back into the same form. It's just a purely matter of manipulation, and it's very easy to do. We just observe that these two terms can be merged like that, as a looks like a product term, right? But it isn't quite right, because you see that the downshift over here is stuck inside P1 and P2, whereas to be in canonical form, the downshift should lie between P1 and this I minus RZ inverse. So we need to pluck the Z downshift out of there and the Z downshift out of there. So what I do is I insert a permutation matrix S in between, and then just observe that if I pick S to be the perfect shuffle, it all goes through. Okay, if I picked S to be the perfect shuffle, for example, this equation holds. This Z is, of course, not that one. Okay, it's a block diagonal version of that one, so a little bit of abuse of notation there. But it's another downshift type of matrix. You plug it in, and you can see that everything, this Z to 1 Z2 can be moved out. It can be called P3. That one can be written like this, and so on. And this gives you the fast algorithm without any further ado. Okay, so you can write, and you can then, once you figure it out, you can see that, oh, the two P's go side by side, the two Q's go side by side, and the R's go on the block diagonal like that. Because we know the rank, SSS rank is going to increase, so the number of columns in the P's and the Q's must increase in this way, right? This is, of course, a very trivial algorithm, right? There's no calculation was done. We were just assembling the pieces back together. So it's just no operations were done at all to do this calculation, right? Of course, this would have been more trivial to a systems guy. This would have been more trivial by just saying it's a state space approach. Since you're multiplying by A and B in parallel, you carry the state space in parallel, so therefore you're just parallelizing the state space. Okay, that's how they would have said it. But anyway, this is just by algebraic manipulation. All right, next is the more complicated operation. If you want,
So can I ask,
yeah, definitely.
I'm lost.
Sure, sorry.
Just because, and I've seen this before.
Okay, that's really bad on my part. Okay.
When you subtract two matrices, the rank can drop.
Yes, it could. This is not minimal. Yeah, see, you see, when I form these two, I'm not claiming that this representation is minimal in any way. It is, it satisfies the upper bound, which is at most the sum of the two ranks.
But you sort of claim that somehow this representation gives you a numerically stable inverse. But if
We
the
haven't.
rank drops, if the rank drops, you lose the stability.
We don't lose stability with the rank drops, but we do gain inefficiency in the process. And there's actually an algorithm we normally run called model reduction, but we'll go ahead and compress this. But when we run model reduction, the problem is that we have to use some tolerance to say when something is small or not. So I didn't want to bring those issues into this community.
No,
Yeah.
I mean, if you subtract two matrices, you can get the zero matrix.
Definitely.
And you can no longer.
Yes. Yes.
So somehow, how can it be numerically stable if it has no solution?
As always, so when we talk about numerical stability, there's always some bound in the condition number we need. Numerical stability, even for dense matrices, is not a free-for-all. So we normally require, for example, the condition number of the matrix A is smaller than some n squared times mission position. So we need some bound.
But this is a numerical rank. It's not. It's a rank. It's not.
This is the numerical rank of the off-diagonal block.
Condition number on the entire matrix.
It is not, and it doesn't affect the stability at all. So this is the numerical rank of the off-diagonal block, which has nothing to do with the condition of, has really no effect on the condition of the overall matrix. And it does not affect the stability of the algorithm I'm going to talk about. So say, for example, the rank was 3 and I use a rank 4 representation. It has nothing to do with the stability.
So your argument is if you do a subtraction and you lose rank, you lose conditioning, and therefore you can declare your algorithm.
No. So this is the rank of the off-diagonal block. So if I go back, so this rank is the rank of, let me go back one more. So this is the rank of this block over here, right? So if that rank was actually 0, but I thought it was 3 at most, and I used a rank 3 representation, I don't make my algorithm on inverting this guy unstable. I just become a little bit more inefficient. So using 5 flops, I'm using 10 flops. Right, you subtract 2 matrices, and this rank drops to 0, for example.
But what happens on the diagonal?
It is, if something happens in the diagonal and this whole matrix becomes ill-conditioned, then you're in trouble anyway. Right? So the diagonal is just being subtracted, just like A minus B is normal. There's no instability on the diagonal itself, right? We're just doing ordinary subtraction on the diagonal entries. We're not doing anything special on the diagonal. That's why I don't talk about the diagonals at all in this representation.
So subtraction cannot affect the diagonal.
It does affect, right? If I do A minus B, I subtract the 2 diagonal entries.
And you assume that you still have diagonal dominance.
We don't assume diagonal dominance because the algorithm I'm using is a QR factorization, which does not depend upon the matrix being diagonally dominant to be stable. So you see that when I finish embedding over here, I'm reordering this matrix into a block tridiagonal matrix and then just doing QR factorization on it, which respects the condition of this larger matrix actually. And you can show that the condition of this larger matrix is really a constant away from the condition of the original matrix A, as long as you use what's called a proper form. So proper form requires that these, okay, now I'm getting into numerical stability issues, but he brought it up. So what depends proper right, so proper form means that these R's and these W which are being multiplied together must have norm at most 1 in some submultiplicative norm. As long as you can guarantee that, you will get numerical stability. Okay, so to get that, when we're in the construction phase, so remember when we were in the construction phase over here, okay, so now in control theories we would call this either left proper form or right proper form. You must pick either this one or that one to be an orthogonal matrix. There's a further constraint that's placed in practice to ensure that that all these W's, because remember this will be an orthogonal matrix, all the W's will be smaller than 1 in magnitude. Right, that's how it is done. Right, so there's obviously a lot of details, but to make it.
But I'm still confused. If you do a subtraction, you can also introduce instability in the QR factorization. It's not restricted to the LU factorization because you can have cancellation.
Right, of course. That's why it's always in terms of backward stability. We're saying there's a nearby matrix for which you have an exact factorization. Right? If I subtract 2 matrices, I can put the errors back in the original matrices. Subtraction is backward stable. It's the exact subtraction of 2 nearby matrices. And you can show something similar over here too. But the way we're doing it, you're guaranteed that you're getting the SSS representation of 2 guys who are close to the ones that you started with. Not forward stability, but backward stability. That's the best you can hope for, right? I mean, no matter what, that's where we are.
No, I don't think so. This is what you say. This is not true. You can do a single logarithmic decomposition, and it's not true that backward stability is the best you can hope for.
Single value decomposition is its own can of worms too. I mean, even there you have to make a rank decision, right? I mean, if you do, for example, LU factorization with complete pivoting or a rank revealing pivoting, you get almost SVD, so off by some polynomial factor.
I stop now.
Okay, we can talk about it.
I want to tell you, I'm not satisfied by that.
I'm happy to hear that. we can have a good discussion. Okay, so this Fast matrix, until I'm pretty much on time, I think. Okay, so let's do we did add. This is an algorithm for the add. We're doing an exact arithmetic. You don't have to question me. All right, and there's an algebraic technique for doing it, so trivial algorithm. Okay, so now let's do multiply. We want to multiply two matrices in SSS form. And what is nice to observe is that we multiply A and B, so their Hankel blocks are shown one Hankel block A01, B01. You notice in their product, you get a term like that in the Hankel block, and you just tell the product, you can see that the ranks are going to be at most the sum of the Hankel block ranks of A and B. So therefore, if we start with small ranks, you're going to end up with small ranks in some sense. So the question is there a fast algorithm to take the SSS representation of A and B, produce the SSS representation of A times B? Okay, and since you brought it up, I'm also going to point out that even in floating point arithmetic, the product of two matrices is not backward stable. Okay, so matrix multiplication is in general something to be avoided if you're worried about numerical stability. But anyway, I'm going to give you an exact algorithm here. Okay, so the way I'm going to do it, I'm going to split it up. I'm going to assume that you split up into strictly lower triangular, strictly upper triangular, and strictly diagonal. So there are 4 terms to multiply. I'll just concentrate on multiplying the two lower triangular parts, strictly lower triangular parts. Okay, so here's the first term in diagonal form, and then I'm first doing lower times upper. That's the easier one. So I'm multiplying the strictly lower triangular part of one matrix with the strictly upper triangular part of the second matrix. So one uses P, R, and Q from the first matrix. The other one uses U, W, and V from the second matrix. Okay, so that's the diagonal form of the lower part and the upper part. You can see that by the Z downshift here and the Z downshift transpose up there. Okay, that flips it from lower to upper. Right. So this is a technique that I did not invent. It was shown to me by Patrick DeWilde. He showed that the way to think about this guy and to rewrite it is to think of ordinary partial fraction decomposition, partial fraction expansion, right? So that Z up there is deliberately chosen to mimic the Z in complex analysis, right? So if you think of Z transpose as being Z inverse, you're roughly in the right ballpark. Then this is the partial fraction expansion that you want to think about, right? So we're going to try to mimic this partial fraction expansion. Of course, in our case, Z and Z transpose don't commute with each other, right? They're off by rank 1. So we have to be a little bit careful with the algebra, right? So my ansatz is that I ignore the PZ and the V from the top, right? Because they're not invertible matrices. I just take them away. And I look at the inner part, which is this piece over here, right? And I'm going to try a partial fraction expansion of this particular form. Notice that we lack commutativity, so you must be careful where you place these extra terms, right? So I've written the partial fraction to sort of mimic this one over here. That's what I'm going to do. So I want to find diagonal matrices A and B that satisfy this equation. Okay, this is critical. I want A and B to be diagonal. If they're not, then I cannot get the form back like this. All right, which is what I do. So again, you do the usual partial fraction expansion now. The inverse is on the outside, so you can multiply, expand, and solve. If you do this and compare terms, you'll see A has to be chosen to be that matrix. And then you plug A back in, you'll get the single equation for the unknown coefficient B, unknown diagonal matrix B, block diagonal. Right? So you see that this one is a tangled mess, so you try to solve this B just like in the regular partial fraction expansion. And if you stare at this really, really hard, you'll see that this is the recursion for solving for that diagonal matrix B, this recursion over here. Okay? So that is the intermediate calculation that you need to do to multiply two SSS matrices. Because it's purely algebraic manipulation, you get this. Once you have the B's, then you can get the A's in terms of the B's, and you notice that that Z downshift transport makes it back into a diagonal matrix, even though it doesn't look like it. So you get diagonal matrices back out. So once you have A and B as diagonal, then you can write this like that. Okay, plug the A's and the B back in terms of A and B, you can't simplify the A and B, but the recursion for computing A and B is linear. All right. So once you have A and B like this, you're almost done, right? So this looks perfect. It's definitely the lower triangular part. However, this looks a bit wacky, right? There should be a single Z transpose over here, and we have this mess over here. So we need to a little bit fiddle with that term. We just observe that you can write that trivial identity up there, and you get an extra Z transpose. So the second term is up here. I plug it in over here and expand it out, and now I'm done. Okay, so this is a diagonal matrix, and I'm in canonical form right now, and that's the fast algorithm. Okay, I know this is like either looks like too much or too little. You can also do it by brute force, okay? But I wanted to present the algebraic approach over here because very few people know about it. It's like a few lines to derive these algorithms. And this algebraic approach is missing when we go to the other graph structures. So one of the open problems is there similar algebraic calculus for these other representations too? I don't know. Okay, for this one works. Okay, next. Okay, so you can now take all of that and write down the representation of lower times upper explicitly if you wanted to over here, right? And we notice that we multiply a strictly lower triangular with strictly upper triangular. The SSS rank does not increase, as you can see. They all are still R by R matrices inside the diagonal. All right, so there is no increase in SSS rank. We multiply lower times upper, which is kind of strange. Okay, next, I'm going to look at the inverse of a lower triangular matrix. Lower times lower is actually easy, so I skipped that one. So I think I skipped it, at least in the slides. Am I almost done? I'm down to 20 minutes. I should speed up maybe. Okay. So similarly, there's an expression for the inverse of a lower triangular matrix, right? So if I take the inverse of a lower triangular matrix, I can write it like that. That makes it clear that the Hankel block ranks don't change for the inverse of a lower triangular matrix. And again, you can do some diagonal algebra, and you can find the representation of the inverse of a lower triangular matrix given the SSS representation of a lower triangular matrix. Okay, I'm not going to go through it. It's just the matrix inversion lemma in this case. Right. So now, what about the LU factorization? So assuming it's diagonally dominant or whatever, how do you find the LU factorization? Again, you notice that if I take the block LU factors, it's very clear that the SSS rank of L and the SSS rank of U is the same as the corresponding SSS ranks of A. The upper rank goes to U, the lower rank goes to L. Okay, so there should be an efficient way to do this too. You can try to do the algebraic form over here, but it seems to be a mess. So I'm going to propose just present the way Ming at Berkeley did it. And since I'm running out of time, I'm going to a little bit speed up now. Okay, I want to talk a little bit of HSS too. So the idea is very simple in this case to observe the recursion. What you do is you first add to the matrix A, you add an extra term that combines the SSS representation of the lower part and the upper part with this coefficient matrix C0 in the middle. All right, in the beginning you pick C0 to be 0, so that the matrix B is actually the same as the matrix A, but mentally in our head we say, okay, C0 is not 0. And then we observe that if I look at the first row, column, and row of B, it looks like this. Okay, so it's still an SSS matrix. If you were to tweak the last term in the first column and the first term in the first row, right? If you tweak it, it's still an SSS form. It just looks a little bit funny, right? And what is nice is that this form is preserved in the gas elimination. So, for example, I need to compute the Schur complement of this, right? When I do LU factorization on this matrix, I need to compute the Schur complement of this little block over here. So that's the only part that I'm looking at, right? And the Schur complement of this part is this column times the inverse times that row is what you add to this matrix, or subtract from that bottom matrix over there for Schur complement. So that's what I do. Right? This is what I have to do. So if you look at it, this is the whole expression, right? This is the term that was already there on the right-hand side. That's the original matrix A. This is the extra term that I added with Z0. And this is a subtraction that we do to find the Schur complement. And if you stare at this, you see that it actually can be merged back into a term of the original form if I define C1 to be that expression. And C1 can be computed in P-cubed operations. Okay, so remember there's no n in this, unlike the Schur algorithm. We do it in R-cubed operations, so therefore the whole algorithm is just linear. All right, from this we can actually compute the inverse using all the formula that I said previously. Okay, so I'm going to skip that. Okay, so that was the SSS representation. It's definitely much more uniform. A lot is known about it. Maybe I would say the open question about SSS representation is that if a matrix has small Hankel block ranks, what can you say about the eigenvectors of this matrix? Right, that seems to be fairly, and I would still categorize it fairly as an open problem. Okay, so now we go to the HSS method. So the SSS method is very good for one-dimensional problems in some sense. Okay, so sort of like Topless, Cauchy, Veneman kind of class. It does not generalize well to sums of tensor products. So since that is the dominant thing in engineering calculations, so people have proposed other things, and I'm going to talk about one of those methods. Okay, we sort of represent, as far as I know, the almost the end of the road in terms of, I'll make it clear what I mean. Okay, so HSS matrices. So this matrix representation was born in computation involving potential theory. So for example, this is born from what's called the Fast Multipole Method. One of the authors, of course, who's from Courant, as part of his thesis work, Leslie Greengard. So this is Greengard and Rokhlin's Fast Multipole Method. So basically, the Fast Multipole Method has to do with sums of this form. Okay, so I'll give you the points xi and yj, and I give you the numbers qj, and I want you to find the numbers pi. Right, there are n of every one. There are n numbers in every category: n x's, n y's, n q's, n p's to be found. Now you can see this is the kind of sum you get in potential theory, and you want to find the p's quickly, right? If you do it slowly, it takes you n squared operations, and the question is, can you do this fast? So the Fast Multipole Method is an approximate algorithm to compute p in n log n operations. Okay, the HSS that I'm going to talk about is an algebraic formulation of this method, but it does not require any understanding of analysis at all. Okay. Now, the Fast Multipole Method is only concerned with the corresponding matrix vector multiplier. You can see that's clearly a matrix vector multiplication going on there. It says you put all the q's in a column and all these xi, yj's entry in a matrix A, then you're trying A times x, right? So this is the entry A. How to multiply A times x quickly. Of course, what we care about in engineering practice is how to apply A inverse times x quickly. Okay, that's the most hard calculation. We want that one to go fast. Okay, unfortunately, it turns out that the full representation that they use, the FMM, is hard to invert. We're still understanding how to do it properly. There are lots of papers about it. But there's one special case where we can do it all by hand, like as cleanly as SSS. Okay, and this one special case is called HSS representation. Okay, so what is this special case? So this special case can be related back to the SSS representation by saying that we're going to look at a slightly different class of Hankel blocks. Okay, so for SSS we use 2 by 2 partitions. For HSS we use 3 by 3 partitions. The diagonal blocks are still square blocks. Okay, so that's important. But what we care about are the middle blocks, middle of diagonal blocks, A01, A10, A1 to A21. And what we care about is not the rank of each individual block, but of them pasted together. So for example, if I take the 2 column blocks and paste them, I get this block, which I call the column Hankel block. If I take the 2 row blocks and paste them together, I get RL, which I call the row Hankel block. And what the HSS rank tries to do, is tries to capture the low rank structure of these Hankel blocks. However, there's one caveat though. It does not try to capture the ranks of all of them. Okay, this is not super important now, but when you try to generalize, it's important. It doesn't try to capture, like SSS captures the low rank of every Hankel block. Okay, this one picks a slightly different class of Hankel blocks we call row and column Hankel blocks, but it doesn't use all of them, which complicates the representation somewhat. Okay, so best to do it over here. So what we do is we partition this matrix first. Okay, so n00 is n, it's a total number of columns and rows in the matrix, say total number of columns. I partition it at n10, n11, so these 2 numbers add up to that, and I partition this like this. Okay, so it's called this hierarchical partition. Right, there's a better picture of it down here. See, I partition the matrix, so this is n10, n11, and then I partition it again like that. Okay, so this is a nested partitioning of the matrices is going on. Right, and then once you pick the partition, I can use any one level. Say, for example, take all these numbers in the last level, and I can use that to completely partition this matrix in tiny little pieces. Okay, so this is called the kth level partition, and my first index says which level of the partitioning tree I'm using, and the remaining are just the usual row column indexing of the block partition matrix. Okay, so it's just a complicated thing. Okay, so if you talk about the row and Hankel blocks, there's a row and Hankel blocks only at these partition levels that I look at. Okay, so I don't look at all of them, only by this prefixed of partition. For example, for this partitioning, this is the valid row and Hankel block, so they can be pulled. So this is 1 row Hankel block, and this is 1 column Hankel block. Okay, notice again that I skip the diagonals, because the diagonals in general will be not low rank, they're skipped in this representation. All right. The next thing is to observe is that if I look at row and column Hankel blocks in 2 adjacent levels, they do actually overlap. For example, remember here, for example, this one is the thick one at the 2nd level. At the 3rd level, it is this one, this one, and this one, this one. So in the previous one, I used these blocks and these blocks, right? So I have to drop these 2 from the smaller level. Okay, there's this overlap again. And what you want to do is to find a representation that captures all the low ranks again perfectly, okay, and exploits all this overlap correctly. Right? So you won't be able to go back and forth. And the FMM representations do this for more complicated partitions, but the HSS representation does it for this particular style of partitioning. All right, so how is the representation chosen? Unlike the SSS case, the FMM representation is actually a little bit easy to understand. Okay, so what we do is that for each of the row Hankel blocks like this, we find a column basis, which are called the U's. Okay, that's easy to think about, right? There's no magic. And for each of the column Hankel blocks, we find a row basis, which we call the V's. All right, so those are the U's and the V's. Okay, then once you have the U's and the V's, right, you have full column basis and a full row basis. Then for any block, you can expand in terms of the U's and the V's. So, for example, if I pick this block over here, then U23 definitely spans the columns of this block, right? And V22 definitely spans the rows of this block. So for this block over here, I have a matrix which I call B2, 3, 2, which are called the expansion coefficients that's sitting up there, right? So it's very trivial. Okay, the HSM is just straightforward, undergraduate linear algebra, so it's easy to do. The one caveat is that because these blocks are overlapping, the U's and the V's are not independent. Okay, so for example, this U is related to the U for this Hankel block too, because they overlap, right? So in particular, you don't need the U for this Hankel block if you have the column basis for this Hankel block and this Hankel block separately. You don't need it. Okay, so therefore we capture that by saying that if you have U at the level k plus 1, then you don't need the U at level k, provided you know how to paste them together using these translation operators R. Okay, these R's were called translation operators because in the original FMM paper, these bases were either polynomial bases or rational bases, so multipole expansion, right? So multipole the rational functions, and you had to move the center of the Taylor series from one place in physical space to another space. That's how you merge the blocks. And so you have to translate the Taylor series. They're called translation operators. Okay, and that name stuck. So now these R's are called translation operators, and same thing for the row bases. These W's are called translation operators too. Okay, so with that, we have the complete thing. Okay, so for example, here is using all the U's, all the V's things. So this is not the right HSS representation, right? Because it doesn't use any translation operators. Here's the same thing in more pictorial form. Again, I never store this U, okay? Because I have these two U's, I can compute this from these two guys. So this U is a column base not just for this part, but also for this part. Okay, that's not clear from the diagram, but it is. Okay, that's how. So this complicated overlapping pattern is used. Right. So because of this, I only have to store. I have 5 minutes. So I have to store the U's and the V's and the diagonal blocks at the leaf nodes, at the smallest partitions. And above that, I only have to store the translation operators and the expansion coefficient for every node. Right? So I have to come back over here. I have to store the B's for everybody. They're all independent. That would be stored. Right? I have to store the main diagonal blocks. I have no choice. I have to store the U's and the V's at the leaves. And then I need the translation operators to compute the U's and the V's as I go up. So typically it's denoted using this graph. And this graph will turn out to be the main guy. Okay. So now the construction is like what I explained to you, so it's very easy to do. In special cases, of course, you can construct in linear time. And for many people, the fast multipole method is synonymous with the construction algorithm. Okay, if I give you the kind of example I started off with, how do you construct these U's, V's, B's, and R in linear time? That's called the fast multipole method. As you can imagine, it has mostly things to do with analysis and potential theory, so we will not talk about it in this thing. Okay, how do you do matrix vector multiply? The matrix vector multiply is quite trivial in this case, because you see that we have this low rank partitioning. So you need to multiply this big low rank matrix with the bottom part of the X that you're multiplying, exploiting the low rank structure like I said before. So it's fairly trivial to do, so I'll talk about it. So you need to multiply V times X to get the G. If the V is available, you have a sufficiently small block, then you multiply by V. If the V is not available, then it can be composed with translation operators from a final level V. You multiply it out and it can be written in terms of the G's, which are these guys, from the lower level. So these are called the upsweep recursions to find V transpose times X. They give you all the G's. Then once you have all the G's, then you have to go back, right? Once you have all the G's, you have V transpose X, V transpose X. You need to multiply by B, multiply by U, and then add it to the output, right? But of course, you don't have these U's to multiply by, so you have to be a little bit careful. So we give them some intermediate names. Okay, so that's where it is. So you see, to get a B, you need to multiply by the diagonal block plus U times whatever stuff is there. Okay, that stuff is complicated to describe, so we call it F. All right. So to get that F, what do we do? Right. So this part is a little bit tricky. So you look at the root node first. A times X should be B, right? And here it is in the partitioned form. So this F is initially 0, an empty matrix, if you think of it like that, right? So if I go down one level and ask how is the upper part of the B computed, then I can expand it all out in terms of the HSS thing. And you'll see that now the new F should be described by this expression over here. Okay, it's just some algebra, but you work through it. Okay, so this is by brute force. Okay, like I said, I don't have any clever algebraic technique to do this, so this is just brute force. You observe this pattern, and then you guess that this should be the recursions, and then you plug it back and prove by induction. Okay, so this is the downsweep recursions for the F's. The F's are what go in front of the U's, such that A times X plus that will give you the right output vector. Okay, and the F's can be written in terms of the G's and F's at a higher level. This is the outsweep recursions, right? And this is the full recursion for doing matrix vector multiply for an HSS matrix. Right, so the G's go up the tree, the F's come down the tree, and then you come to the very bottom, you can actually compute the B's. And you can see that each part of the recursion requires only a P by R by R matrix at most. There are only a linear number of recursions, right? So in the end, this comes to be something linear in cost, right, if you do the calculations. All right. Right, and here's the signal flow graph for this, right? And again, signal flow graph will actually tell us everything. So the axes are partitioned, the inputs are sent into this. You compute the G's as you go up. When you reach the top of the tree, you compute the F's and come down, and the G's flow to the right and left using the B's. And then finally, the outputs B's are computed at the bottom. Okay, so for the HSS matrix, the signal flow graph is not a linear graph. It is this perfect binary tree instead, right? And these graphs actually have a special name because see, there's no edge between these two guys. That's critical. So this graph has a perfect elimination of.
This is a preconditioned method, right?
No.
Linear time after you have processed the model.
If you have the HSS representation already, it's linear time. You can get the HSS representation in linear time for some class of problems using the fast multipole method technique. For other class of problems, you have to use this n squared algorithm to compute the HSS representation. So depending upon what your matrix looks like when you start. So for example, if it's a Cauchy matrix, then in linear time, you can compute the HSS representation using the FMM techniques. I have almost time. Okay, so the key thing then is you can convert these recursions using these downshift operators. I'm going to skip this fairly fast, okay, because I'm out of time. You can write the whole recursion using these diagonal matrices again into sum of 3 terms. Okay, so these are the G's, F's, and the B's, and the X's are the going in. And you can assemble them into this matrix, which is not arrowhead anymore, but it is special. It's the sparse matrix for that is that binary tree that I showed. If you eliminate in the wrong order, so you eliminate G and F, and you get X, you get the so-called diagonal representation for the matrix A. It's much simpler in this case. There's only one term because we don't distinguish between upper part and lower triangular part for the HSS representation. However, the downside is then that this is a triple product. It's got a Z downshift on the tree and a Z twiddle, an exchange operator on the tree too. Okay, so it's much more complicated algebra. There are 3 variables involved rather than Z and Z transpose like before, which almost commuted. You get this messy stuff instead to do with. You can actually do some algebra on this guy too, okay, which is surprising, but it's a royal mess. I never published it. So the solver just consists of showing that the sparse matrix for that guy is this matrix, this graph over here. And this graph, of course, has perfect elimination order, right? If I eliminate this node, you get no fill-in. Then I eliminate this node, no fill-in. Eliminate this node, no fill-in. Eliminate this node, no fill-in. And I'm left with a smaller tree. And then you do that again. And of course, if you do QR factorization on this graph, again, there's no fill-in. So you have a numerically stable algorithm. Okay, so among the FMM family, as far as we know, this is the one thing, this is the only graph that has that property. None of the other FMM trees have this property. There are also algorithms for doing fast multiplies. I skip over it. fast LU factorization. Again, all of this is by brute force, okay? So I'm not going to talk about it. Fast inverse. Again, all I know is brute force basis. It's not all entertaining to look at it. And similarly, you can show the inverse of an HSS matrix has the same ranks as the original matrix. So the column and row Hankel block have the same ranks, and there's an efficient way to theoretically efficient way to find it in that case, right? And there are lots of open questions in this, and I'm coming to the end of my slide. The only thing that I want to add is this. The question that people care about a lot in this field is that, okay, if I generalize this graph to something more complicated, right? So if I have more edges or something like that, then I want to find the inverse of those matrices quickly. And the question then becomes, so now we're using a much more complicated partitioning of the off-diagonal blocks. So for example, if I come back to my pattern over here, okay, so let's look at this, right? You see that this whole entire off-diagonal block is taken as one giant block, right? And that being low rank is extremely unlikely in practice, not for engineering problems. So we care about further partitioning this block into pieces, and those pieces are going to have low rank. So that's the full FMM partition. That's it. We have a more complicated partitioning of the off-diagonal blocks. Now the question is, for that class of matrices, how do you compute or how do you apply the inverse quickly? Right? That's the big thing. So right now it's mostly heuristical work, some proofs in special cases, like if the matrix came from a Laplace or matrix or something like that, we can prove some things. But in general, the exact inverse, how do you characterize the exact inverse? What does it look like? What is the pattern? We don't know about those things. I gave a talk about how to generalize this stuff to other graphs in a workshop in linear algebra last month, and you can find it on my website, which is somewhere over there. Where is it? There. You can find this talk I gave at the Applied Linear Algebra conference and thing. And there are lots of open problems, and I'll be happy to discuss with you what I think are the one that at least that interests me. Thank you. My time.
Matrix time vector for that. And the nice thing about the theory of Topless-like matrices is that those two complexities are the same.
Definitely.
But in this generalization, I always have the suspicion they're not the same.
It may not be the same.
Quadratic preconditioning and the linear. Is that true? Is that impression true?
It's definitely true in some cases. For example, if the matrix A is a general matrix, which you suspect has low rank in the off-diagonal blocks, then in general you have nothing, you have to sweep through all the entries in the matrix at least once, which means that the best you can hope for is an n-squared algorithm. And that's how the algorithms are fashioned. Now, if the matrix is structured and you know something about the matrix beforehand, then there are the fast multiple techniques that work in linear time, n log n time or something like that. Or the matrix is sparse. For example, if the matrix is sparse, then in general you can write down the FMM representation in linear time. But those are the two typical starting points for engineers, at least. For people like me, we usually start with a sparse matrix, and then we're doing Gauss elimination on it, so then it becomes dense. But since I started with the sparse matrix, I already know the FMM representation before I start in linear time, so it doesn't cost me any further after that. So that's how it is for me in practice. For other people,
so for you, the cost of preconditioning is not the focus. So you
it hasn't. No. Linear time, because I'm starting with a sparse matrix. So I have a big sparse matrix, right? And I want the FMM representation of that, but I can write that down in linear time, like I did it for the tri-diagonal matrix. I wrote down the SSS representation by just looking at it. It doesn't cost me anything, because the only low rank in a sparse matrix is due to the zero structure, which is easy to capture. You can do calculations by hand, so it doesn't matter to me. But there are definitely algorithms like randomized algorithms and stuff which try to make the n-squared cost bearable. That's the best I can say. Sure.
So you kind of hide the exponent in the R factor in the
Yeah, sometimes.
computing with the HSS and some SSS structures. So as far as I understand, HSS matrices allow you to apply a vector in O of n R squared.
In R it should be.
N R, sorry, yes. And in SSS it's O of n R squared.
Should be R again. If you do it, yeah.
So the two representations are equivalent in terms of complexities?
Yeah, we assume the rank is constant, it is true. So when the problem is, the way they, in actual computations, we don't want to work at the scalar levels. We end up with some block that we stop calculations on. So if you choose the block size correctly, then you get the overall complexity should be the original slow algorithm's complexity. So you have n to the power C1, R to the power C2, C1 plus C2 should be 2 for multiply and 3 for inversion or factorization. That's how, if you do things right, it should always come out that way. In other words, as the matrix becomes full rank in the off diagonal, you go back to the standard slow algorithms. Unless you do a Strassen style acceleration. If you do a Strassen style acceleration, then you should go to the right optimal complexity. And Victor Pan has papers saying how do you arrange the calculation so that you can benefit fully from the Strassen style acceleration if you need to do it.
Well, there's no other question. Let's thank our speaker again.
Thank you.